Oh, yep.
So
There we go.
I
Oh,
did it twice. Sorry.
okay.
Sorry.
That's okay. We're fine.
Oh, sorry. Yep.
We're gonna do that.
Sorry, I didn't mean to have
Okay.
much stress.
We're good. We're good.
Thank you.
Okay. We're back. So, all right. So today I'm going to focus on one of the main shell heap sites of an archaeological complex on the coast of Peru known as the Ostra Collecting Station. As a quick side note, one way archaeological sites can be named is from a prominent feature, which is the case here. So a shell heap refers to a type of site created through the accumulation of discarded shells, and ostra is Spanish for oyster. A few of which I have placed circles around. These oysters make up the majority of the shell heap matrix at the site. So the Ostra collecting station, indicated in the right image with a red star, is located on the north-central coast of Peru. The Andean Mountains are directly to the east and act as a formidable barrier. It's been radiocarbon dated to 6100 to 6600 calibrated years BP, and these radiocarbon dates overlap with the radiocarbon dates of an associated site about 5 kilometers south known as the Ostra Base Camp, which is indicated in the right image by the white star. The Ostra collecting station site itself is in an interesting and strategic location and has some curious things going on. So visible in person when you're on the ground and in aerial imagery, as outlined in black in the left image, is the ancient shoreline. The site is located at the top of this ancient sea cliff, which is located along the edge of the ancient shoreline. And we know that the ancient shoreline dates to the same age as the site because of Keone shells found in living position along the shoreline at the base of the site with radiocarbon dates that align with the radiocarbon dates of the site. In present day, the Pacific Ocean is located about 5 to 6 kilometers to the west of the site, depending on where you are along the shoreline, and this would have acted as another formidable barrier to the west. If we zoom in a bit closer to the site, at the top of the ancient sea cliff are the remains of an approximately 8 by 9 meter granite stone structure, roughly outlined on the image to the right, with a granite wall fall depicted in the top right image from excavations carried out in this corner in 2018. As far as cultural materials recovered from the site, I'm going to focus on one type of artifact known as sling stones. These are stones that are clustered together in piles, like the ones shown here in these images. The piles each consist of about 100 water-worn, rounded rocks about the size of your fist. There are about 60 piles of sling stones spread across 2 lines. A northern line, located on a more flat surface, and a southern line located along the top of the ancient sea cliff and extending out east from the structure. The distance between these 2 lines is 179 meters. So here we have a section of the southern line of sling stones showing 9 different piles. This is the line that's along the top of the sea cliff, which extends east from that structure. And it was captured using a LiDAR option on an app on my phone. So here we have 6 examples of different types of sling stones found within these piles. The rotating models are some of the ones that I've captured in the field using photogrammetry. And these can be exported from the app under a variety of formats. We also flew a drone over the site to create a digital elevation model, which can be used for many purposes. One such purpose is being able to convert the DEM so it can be imported as a base layer in a simulated environment, complete with accurate texture and colors. So reconstructing archaeological sites in virtual reality allows users to experience the site from afar. To create this world, I've been using Unity 3D game engine. This is a screenshot from my simulated environment. The perspective is looking east towards the Andean Mountains, with the red arrow indicating where the 8 by 9 meter structure is, and the Pacific Ocean is in the lower right. As you might be able to imagine, the space is quite large, and it would be both labor and storage intensive to capture every angle of the entire site. So we decided to target specific areas of the site to capture what we felt were important to represent, including the slingstone piles. But before we can get into that, we have to do some physics to answer a few questions. So the height of the sea cliff is about 15 meters. The optimal and most likely angle of release of the stones is 45 degrees. Based on modern slingers data, the average speed of a released stone is 150 kilometers per hour, which converts to 42 meters per second. And the acceleration due to gravity is constant at 9.81 meters per second squared. So what can we do with all of these variables? We can plug them into a series of equations. The first is solving for the maximum height of the arc of the stone. Then, using this result, you can solve for the total time it takes for the stone to land after being released. Finally, you can use this result to solve for range, or the maximum distance that the stones could travel. So why is this important? So the two lines of slingstone piles, if you recall, I said the distance between the two lines was 179 meters. I believe this means that the Ostrins were intentional with the distance and strategic in the placement of these lines, as 194 meters is the maximum range under ideal conditions. So what does this look like when it's simulated? For orientation, we are looking east. The 8 by 9 meter structures on the right side of the screen is indicated by the red arrow. The Pacific Ocean, as indicated by these two red arrows, has been put back to where it was during occupation. The northern slingstone line is in the lower left, as indicated by the black dashed line. And the southern line is indicated in the top right by the red arrow. I'm not sure if you can see it on here, but there is also a line of about 10 slingers up there. The red bar represents 179 meters, which is the distance between these two lines. And outlined here by the thicker black dashed line is the potential striking range of the southern line. So now that I had the correct variables, my friend RJ at the VEMI lab was able to help me plug them into Unity in order to simulate what this would have looked like. This is being shown here in this clip, where the sling stones are exaggerated in size for visualization purposes, but demonstrate the striking distance. Some quick math: 100 stones per pile and about 30 piles per line equates to 3,000 stones of ammunition per line. And that's just what we've identified visible on the surface. So again, why is this important and why did we need to simulate this? To show how psychologically and likely deadly effective of a strategy this was. 3,000 stones raining down on you from above, traveling at 42 meters per second is absolutely terrifying. I think that the Ostrins set this distance between the northern and southern line intentionally so there would be enough overlap to provide adequate cover by the southern line once the northern line had depleted their 3,000 stones of ammunition and were retreating to the southern line. And to leave no stone left unturned. To the east, about 250 meters away from the last pile in the southern line, are a double set of windbreaks. These are C-shaped structures shown in the lower right, whose real purpose and age are not fully understood. I created this model using LiDAR last summer. And what did I find? Rolled away slightly down from the windbreaks, but a slingstone. And slingstones don't get there on their own. So now located directly north and right in front of these windbreaks is a large outcrop, which some might say is an ideal place to hide behind or quite a good barrier. So what happens if we apply the same range? A nice little overlap, which is what I will now be exploring further. With that, I would just like to thank everyone, the Bob and Judy Sturgis Exploration Fund, Dan and Betty Churchill Exploration Fund for funding last summer, which this summer grew on, my committee members, the permission to access the site, and a special thanks to Kate Johnson, who walked a lot of miles last summer collecting data. Thank you. Any questions? Yes.
Great talk. Question I have is about coastline deformations, right? So what do you know about local erosion and seismic uplift or subsidence?
So uplift happened about 4,200 years ago, which is thousands of years after the site was occupied. And that's the evidence that we have of uplift happening at that place. There's a lot more to go into it, which I can tell you about afterwards. It's not an easy summation, but it was a great question.
Great talk as well. I wanted to ask if you had a chance to interview any of the descendants of the native inhabitants in that area. And
We don't know who they are.
Okay.
It's difficult to track that, especially down in Peru. We have an idea, but we don't know the exact descendants of the people who were there at that time. If we did, that would have been part of it. So thank you for bringing that up.
And the area is unoccupied at the moment.
Yes, and the area is currently unoccupied. It's in a big desert. There are mining salt around it right now.
The occupants.
Thank you.
I found the lights in this room. You see the slides better?
Good idea.
I just don't know where it is.
Where?
Which one?
I don't know.
I just know mine or where it is painted. This one? There are ones on that side.
Ooh.
All right.
Didn't even know there was
Okay.
a image. Thank you, thank you. All right. Up next, we have Matilda Burke. She will be presenting on quantifying slope steepening as marine terminating glaciers transition to land terminating glaciers. Go. Thank you. I'm really excited to be here today, and I'm here to present on my thesis work on quantifying the transition from marine to land terminating through 83 years of observations of South Greenland glaciers. And as my title in the program might tell you, the big takeaway is that the glacier slope steepens as marine terminating glaciers transitions from marine terminating to land terminating. And I would like to walk you through why this is important and how I found this result. So if we start in the broad scale, why do we study glaciers? We touched upon this yesterday with great populations being at risk, living in low-lying areas. It can be major cities by the coast or small island states. And it is projected around 0.5 meter of sea level rise by year 2100. A rough estimate is 1 billion people will be living in these low-lying areas. And sea level is rising due to the thermal expansion of seawater as well as input glacial meltwater. So that's where the glaciers comes in. However, why do we study transitioning glaciers, this little niche within glaciology? Let's start with a little definition. Normally, when we study things, we like to put them into boxes. One box we have in glaciology is the marine terminating glacier or tidewater glacier. That is where the glacier is in contact with the ocean. Those are the ones that carve off icebergs and experience submarine melting through interaction with the water. Another box we have, another understanding we have of glaciers is the land terminating one, not in contact with the ocean and where the primary form of ablation is surface melt. We model and understand often these glaciers as two distinct systems, but what I call transitioning is what happens if we look at this as a continuum and where the marine terminating glacier retreats and transitions up onto land. That's the transitioning part. But why is that important? What is its significance? Let's start on a global scale. One study has been modeling transitioning glaciers, and they found, excluding the polar ice sheets though, that by year 2100, 50%, half of all of the world's marine terminating glaciers then will retreat onto land. And another cool thing they did in this Rounds et al. Study from 2023 is they included transition into sea level rise projections, and they got a 2% miscalculation. They found that in the normal approach. And 2% might not always seem like much. However, if we talk about 1 billion people, that's 20 million people, give or take, that suddenly is influenced now. So that's the big picture. However, we know that the consequences are not equally felt everywhere in the world from climate change and its consequences. So if we zoom in on Greenland, the projection is not 50%, but if you look at the peripheral glaciers in Greenland, it's 80 to 90% that will transition by year 2100, which is a drastic change. Because if you have based your livelihood on an ecosystem based on a marine terminating glacier, that with time transitions to be land terminating, you lack then the upwelling mechanism that brings nutrients into the water column and sustain fisheries. So that will have great influence on the local livelihoods of the people who lived near these environments in Greenland. Therefore, transitioning glaciers are important on a global scale and locally. So that's what my research is all about. I'm looking at if we can define the glacial dynamics and geometry and how they change during transition. And what this talk will be about is how I've tried to fill this gap by observation, because we have studies of ecosystem influences and we have modeling studies, but we lack observations and indicators of transition. So if we got that, we can do better models so we can better prepare and predict. Okay, so where is my study taking place? We'll skip this part. It takes place in southern Greenland at Kalalit Nunat, where I study the Kualit Seemat, which is the glacier of the halibut, talking about fisheries. It's retreated about 8 kilometers and transitioned fully from marine terminating to land terminating over the past 83 years. Talking about 83 years, I have an 83 years of observational record, which is really awesome when we want to study a process that's not very well known. We want to study it both while the glacier is marine terminating and land terminating. And through satellite imagery and digital elevation models, we can go back until the 1980s. However, in Greenland, we also have surveys done by the US and Denmark by airplane all the way back from the 1940s during the Second World War. So by combining these aerial imageries and digitize them in Denmark and utilizing structure for motion photogrammetry, you can make dense point clouds that can turn into digital elevation models. And if you want a more in-depth walkthrough of this methodology, I'll be presenting my thesis, hopefully next month. But good to say, I made a model. This is from 1942. I made them all the way up until the 1980s and then extended the record with the Morton record as well. And then the way we use these models is by looking at one glacier. This is one glacier at 3 different time steps. Then we set a survey interval. I surveyed every 25 meters. And from my digital elevation model, I looked at the top of the ice. And by going into the glacier and surveying the depth of the fjord, we can then estimate the thickness of the ice. And suddenly we have a 3-dimensional model of how the glacier looked in the 1940s. Then, looking at these models and thinking about changes in geometry and changes in dynamics as the glacier transitions, we can look at longitudinal profiles, which are cross-sections through the glacier. And to help orient you, each of these lines are different years. But let's take out of the equation for now. And look, this is the bed, this is the ocean. This line represents this glacier, Kualit Seemat, in 1942, as it is marine terminating. And up here, we see it land terminating in 2012. I can see some geometries that differs between these two, just looking at terminus. But to make it more clear, I have stacked these lines. Now they start at the same point. However, we see some more things standing out. Right at the terminus, at the first kilometer, we see some changes, but the slope is more similar further up glacier. However, I have not yet compensated for the part of the glacier that's below sea level. So if we compensate for that and now compare ice thickness, we get a really clear view that up glacier, it's dominated by surface thinning and a stable slope. However, by the terminus, we see a change in geometry where the slope steepens, which would not be possible if we did not have high-resolution digital elevation models that can take all these details and put them into view, because often the resolution is so coarse that you average out the slope over greater distances, and maybe small indicators such as this would be lost. And I did this analysis on the slope for 5 different glaciers for over 83 years, which gave me some really cool results. Because when you look at the glacier, either up glacier from 1 to 2 kilometers, or from 0 to 1 kilometer while it's marine terminating, the slope stays the same. However, when transition happens, suddenly the slope at the terminus really, really increases. And to make this study comparable and just not say that this was just by accident, I also had a study, a neighboring glacier, which was marine terminating for the entire study period. And here we see that's the pink lines. We see no change. We see consistent slope through it all, which, if these findings are generalizable, could make slope a really key indicator of transitioning. So that is what I hope that you will take away from today, that glaciers worldwide are transitioning, but it's a field we don't know much about yet. It has great significance and influence both globally on sea level rise projections, but also for the local livelihoods who are reliant on these ecosystems. And that slope could be a key indicator for finding and identifying these glaciers. And with that, I would like to say thank you to the Bob and Judy Sturgis Exploration Fund for funding and helping with the fieldwork, as well with the Sona NIT, the graduate student government, to Maya and Stine in Denmark in the Danish archives, helping me with the digitization process, the Ice Ocean Lab, my Greenland field team, and my advisor, Kristen Schall, and my committee. Thank you.
So it's cool that you're using such a range of historical data to create the 3D models. I was wondering if you're seeing any like variation in the DEMs or are there any of those data sets that are really crappy for creating topographic models or
Totally. In total, we looked through thousands of imagery. We digitized around 400. We found around 20 sets of imagery, which supposedly had enough overlap to be able to do models, but because of the condition of the film, only 10 of them worked out. So it's a very big funnel working with historical aerial imagery, that some of it is not surveyed in a way that's capable of doing structure for motion photogrammetry, but some of it is also stored on nitrate film, which can self-ignite and decompose, and all of those things influences the results. And here I've only included the digital elevation models, which has a standard and a resolution and an accuracy comparable to modern day remote sensing products. Yeah.
Thank you very much. I'm interested in the interaction between retreating glacier and rising ocean, because as the glacier is pulling back onto land, the ocean may also be rising to meet that.
Yeah.
Is that a dynamic that could potentially sustain these systems, perhaps? Or are they retreating too fast for the rising ocean to account for?
I would say they're retreating too fast and in a place, especially here in southern Greenland, the retreat rate far outnumber the sea level rise.
Okay, thank you.
Thank you. Thank you. Yeah, thank you. Yeah. All right, next up we have Morgan Anderson, and they'll be talking about understanding Maine seabirds as sentinels of global change using guano geochemistry.
Hello, everybody. I'm happy you guys are all here, and I'm happy to be able to talk about my research a little bit, even if it's at 8:30 in the morning. I study seabirds. I'm part of the Gill Lab, and there's a couple reasons why I think seabirds are a really cool system here in Maine. First thing is they connect systems over crazy scales. So on the right side of my screen, I have the migration path of a couple Arctic terns that somebody put trackers on, and as you can see, they connect nearly every landmass on this planet to each other. They breed in the northern Atlantic waters in the summer here, and then go down to Antarctica to feed in the summer there. But through this, they connect huge amounts of area and systems. And they also connect marine systems to terrestrial systems. Most of these seabirds exhibit a life history that looks like feeding a lot on tiny fish out of the ocean, and then breeding and spending time on land. And when they do this, they take nutrients from the ocean and leave them on land. And here in Maine, seabirds are near the top of our food chain. This is a representation of the food web of Maine. And you can see the 3 different categories of seabirds I've highlighted are near the top. There's only a couple of things that are above them on this food web. And because of their position on the food web, they exhibit this thing called biomagnification, where things like trace metals, isotopes, and other subsidies get concentrated as they move up the food chain. So a phytoplankton or zooplankton that only has 10% something in it When it gets eaten by fish in large numbers, now the fish have 50%. Now it gets eaten by the birds eat lots of fish and the birds have 100%. That is a wild oversimplification of this process, but it's something that's exhibited by these birds with lots of different things. You've probably heard of mercury or DDT being a problem in these systems, and it's found in seabirds in big numbers. Because of all these things, seabirds act as strong indicators of what's going on in our ecosystems. Because they reflect changes in climate, both on land and at sea. They are top predators that reflect what's going on throughout the entire food web. They are long-lived, so many seabirds will live for 25 years and return to the same site throughout their entire life to breed. Because of all these things, we can use them as an indicator of what's going on, not just now, but also in the past in systems. And we have a bunch of little seabirds that live in Maine. Here's 9 species that almost always can be found breeding off our coastal islands of Maine, but there's about 25 species that are here at least part-time of the year. You probably heard of puffin tourism in Maine. People really, really like our seabirds, and they're important to people everywhere. They're long traveled. But not only does Maine have cool seabirds on our coast, we also have some interesting climate happening on our coast. This is the map of the world, and I've highlighted our little box of where we are right now. And this is a map of warming trends of sea surface temperature. So red areas are warming the fastest versus blue areas, which are getting colder over time. And you can see we are one of the most red little squares on this map. So Maine is experiencing lots of warming right now. And not only have we experienced this warming now, but we've also seen this in the past. So this is a graph of sea surface temperatures over time. And the 0 on the x-axis of this graph is actually now. And 12 Ka is 12,000 years ago, or kiloann years ago. And you can see all 3 of these lines are from locations off the North Atlantic slope, which is near the coast of Maine. It used to be warmer here. So we're getting warmer, and we used to be warmer, which leads to my question that's central to my master's thesis of figuring out when seabirds were here in the past during this area of climate variance. So we have some information about how long seabirds have lived here, but the oldest record is about 35,000 years ago, provided by our archaeology friends that found a Wabanaki bird flute. But before that, we don't really know, which I would like to find out in my master's. But how do you figure out when a seabird lived here? I've tried asking the seagulls at the parking lot. They've never answered me. And while my whole lab would love a time machine, I'm really far down the list on when I get to use the time machine. So how do you figure out when a bird has lived in an island 5,000 years ago? And the answer is what they leave behind. This picture I have of a colony of double-crested cormorants, which also are found in Maine, is not a fun snowy peak, but that white substance on the rocks is bird guano, or the poop, and it's what they leave behind the most. Some islands will have several feet stacked up of bird guano left behind. And you can use this poop to find a record of seabirds in the past. So right now, my methods for my project is really condensed, as I have 3 islands. I have sediment cores between the islands. So we've taken a sample of the peat bogs on these islands, and I'm going to try to find the chemical remains of bird poop in the past. Today, I really want to talk about nitrogen and carbon isotopes, because that's what I've used my Sturgeon's fund money to go find. So nitrogen isotopes work as a good representation of birds on these islands, because these tiny islands don't have very much going on besides birds and grass. And birds are top predators, which we can see with nitrogen isotopes. Nitrogen exists in a couple forms within our environment naturally. The 15 isotope, which is heavier, and the 14 isotope, which is lighter. And these isotopes exist in a ratio in all living things. And they generally exist with a higher ratio of heavier nitrogen in top predators, because like my biomagnification figure from earlier, as this nitrogen moves up the food chain, the heavy nitrogen is concentrated in living things. So the lighter nitrogen just gets excreted out through natural processes more preferentially. So as you eat more little guys, you get a higher number of heavy nitrogen in your system. And my birds, who are listed either as predators or top predators within our system, are expected to be about 10% on this ratio line. And we'll come back to this later. So to figure this out about my birds, I took my sediment core samples on an adventure, because we don't have the equipment here at UMaine to do this kind of work. So I went and found Dulcinea Groff at the University of Wyoming. She's a previous PhD student from my lab and did similar work in her PhD project, but right now she's working at a stable isotope facility at the University of Wyoming. So you can see my little tubes in the bottom of the corner, and that's the lab we're in. And first, I took my dirt and I ground it up. So you can see my ground up sediment in that tube, and then you put it in a tin capsule. And I put a box around the tin capsule because it's pretty tiny, even in this enlarged photo. You put a specific weight of dirt in this tin capsule, and then you do some tin foil origami to try to make sure your tin capsule is completely closed. And mine weren't the prettiest, so I have on this next screen, mine mostly looked like that. The important part is that your sediment stays contained, not that it's pretty. And then we put it through a mass spectrometer. So mass spectrometer is a big instrument, but it essentially sorts things by weight to tell me which kinds of isotopes I have. The sample is vaporized and then ionized. It goes through a tube with a big magnet and is sorted by weight. So I end up with a signal of how much of these different weighted isotopes I have in my sediment. And for my 2 islands, Iran was in Wyoming, that looked like this, which is a really exciting but somewhat unexpected result. We'll start with the easiest one, and the one I was happy about when I saw it is Ship Island. And you can see most of the core of Ship Island, and we have depth instead of time right now, because I'm still waiting for these samples to be aged, is above my 10 mark that I've decided is birds and based on the literature. That's really exciting. This shows that through the entire age of my core, there was probably birds on this island. I was really happy to see this result. I was a little surprised to see the Petit Banane result because it's wildly variable, which is in science, sometimes we don't get the answers we want, but sometimes those answers are the most exciting. It shows that there's something else going on those islands. There's times where there are high enough signals that I can say there's birds, but there's lots of times where the signals are somewhere in the middle, which is unexpected because these islands usually have lots of plants on them and sometimes lots of birds and not much else. And the plants would be around 2 or 4 on the scale. So what do you do with this information? You get more data. I also ran carbon isotopes, which can be a signal if your carbon sources, like your plants, are coming from marine or freshwater systems, and found similar patterns in my cores. Petit Manan shows the same wild variance in these isotopes, and Ship Island is more consistent and more marine. So I'm going to keep investigating this. You can see both compared here with the rest of my model. So to figure out if these signals are truly birds or something else I'm finding in my bulk sediment isotopes, I have trace metal analysis that is sent off, and I'm awaiting results right now to figure out if these results are truly from birds or something else, because they are several heavy metals that concentrate just in bird systems and not in others. So I'm excited to share those results with you next time. I have some fun photos too. Not only Wyoming did I play with my big mass spectrometer, but I also got taken on a soil coring adventure with Andy Parsakian's lab. They were doing some coring in the Medicine Bow range to try to figure out some things about snowpack. And there's a fun picture of me with their core. And then the pretty mountains. And of course, science never happens in a vacuum. So I'd like to thank especially Dulcinea Groff for taking me on this fun science adventure. This would not be possible without her, letting me come stay in her lab and teaching me and also making me dinner several times. I love when the science works out like that. You make new friends. And I'll take any questions. Yeah.
I'm curious about whether leaching is a problem. The reason I ask is that a little known fact I discovered recently, the US Congress passed a law in the late 19th century that the US had control over every guano island anywhere in the world that wasn't already occupied by somebody else. Yeah, this is true. You can look it up. And there were scientific expeditions, and they found that islands in areas of rainfall basically didn't have much nitrogen compared to particularly the ones off the coast of Peru. This is why I know about it, which is a desert, and it was much better guano for fertilizer because it had a lot more nitrogen. So I wonder if that's an issue here.
Yeah, that totally could be part of the preservation problem of these samples, of why I'm getting mixed results and not just there's birds or there's not birds. It's one reason I'm using other things too. But this method of using stable isotopes to try to find birds is pretty well published on, even in the North Atlantic. They have somebody's done it off the coast of Canada too, a little above us. So I'm hopeful it will also work here. Yeah.
You mentioned that you expect bioaccumulation because they're feeding off of already very highly bioaccumulated fish. Would you expect different signals from different birds who might be feeding from different parts of that accumulation too?
Yeah, I think that's totally possible. So if you think back to my food web, I had 3 different sections of birds on there because there's 3 different main diet classes of seabirds going on. And when Dulcinea did a similar project, she found that through a PCA, that there is some variance in where these things lie. part of my project is I'd like to go out to these islands and collect modern guano from known species and see if I can sort out a species level change, but we don't have good enough data to do that yet. Thanks, Thomas.
Next is Elijah Bradshaw, who will be presenting their research investigating the spatiotemporal patterns of Asimina triloba since the last glacial maximum. Go for it, Elijah.
Good morning, everyone. Yeah, today I will be sharing some of my preliminary results as well as some of my work I did this past field season. My research is examining the role that extinct megafauna may have played in shaping the range dynamics of large seeded fruit trees like the pawpaw. But before we get into the charismatic megaflora, so to speak, some words on the more boring megafauna that may have shaped the landscapes. So we're talking about the megafaunal seed dispersal syndrome, where these fruits that exhibit large fruit sizes, large seeds that may be too large to be dispersed by their contemporary vertebrate dispersers, may have had this coevolutionary relationship with now extinct megafauna. And with the extinctions of the late Quaternary, these fruit trees are what could be known as anachronistic fruits, where they're lacking a primary dispersal mechanism because of the absence of these large animals. Why are these large animals so important for dispersal? This long distance dispersal service that they give to large fruit trees, where we have this nice linear relationship where with an increase in body mass, you see an increase in day range, in gut retention time, and gut capacity. So the larger the animal, the more seeds it can carry in its gut, the longer those seeds can sit in the gut, and the further it will travel to disperse those seeds. So it's more influential in the range dynamics of these species. And so now we get to go to the star of the show, Asimina triloba, common pawpaw, which is a likely candidate for being an anachronistic fruit that may have been, that its range may have been shaped by megafauna because it's the largest berry in the North American flora. And it is also the northernmost species in its family, the custard apple family, which is primarily in tropical systems, where coincidentally, much of this megafauna seed dispersal syndrome research has been done. So this is a nice case study to apply this to temperate systems. And so pawpaw mainly occurs in wet bottomland sites, very close to stream sides in these closed canopy, dense forests in eastern North America. And it can grow as far north as southern New York. And if it's in an orchard, it can go as far as southern Ontario. But where was it in the Pleistocene? We think it was climatically constricted to the Atlantic and Gulf coast zones around the time of the last glacial maximum. And from these zones, so sea level has risen since the deglaciation. So we can't take pollen cores from these areas of high habitat suitability out in the ocean, but from pollen sites further into the coast, we understand that a lot of these areas were potentially analogous to the longleaf and slash pine communities we have in the southeast currently, where we have these very open canopy, pine-dominated pine savanna or grassland systems that were also very fire prone, which is not where we would expect pawpaw to grow. So we understand where it could have occurred climatically, but we want to understand if pawpaw could persist in these conditions. So I have done a seed germination study where we've collected fruits from North Carolina, which is in the core of its ecological range. It's also where I'm from, so I know where the pawpaws are there, which makes this easy. And we ran a series of scarification treatments. So we put a bunch of seeds in the oven to mimic fire conditions to get at that, whether or not it could persist in fire-prone pine savanna. There is a hypothesis that water dispersal is important for pawpaw as an alternative to the extinct megafauna service that it once had because of its streamside obligate habitat. So we soak the seeds in water to get at that. And then we're also testing whether or not gut passage has an effect on germination success. So we've mimicked the seeds sitting in the gut by soaking them in a hydrochloric acid solution. And this brings us to my field work. Being from North Carolina, I feel obligated to tell you that this is the boring part of North Carolina. We're not in Appalachia. We set out to get 12 fruits. We had a great time and got 103 fruits collected from the Jordan game lands. This is streamside habitat, very stereotypical pawpaw habitat. We used the wonderful pawpaw funnel there in the middle to collect seed or fruits high up in the trees. And then we took the seeds out of the fruits and did our germination experiment. Thank you to the NC State Forest Entomology Lab for letting me make their lab smell like pawpaw for 24 hours. We have our model elephant stomach, so to speak, there, the big bucket with our hydrochloric acid solution, put them in the oven, another bucket for the water. And following the 24 hours for this experiment, took the seeds out and planted them in the NC State Experimental Forest. I chose this site because it is very similar to where we collected them from. Again, another streamside habitat with closed canopy. You'll notice the middle picture, different season, we had to go back and put back up our seed enclosures because a lot of deer trampling occurred there. And as a backup, we have seeds in the greenhouse, just in case predation was a problem. In fact, predation might be more a problem in the greenhouse because there are rats in there and they ate some seeds. But happy to report back, this picture is actually dated. We currently have 21 seedlings thus far growing through all of our treatments, which is very interesting, especially for the fire treatment. Did not expect any germination success there, but the seeds can indeed persist through the conditions of a low intensity ground fire. And this brings us to a glimpse of what we're trying to do in the Pleistocene. If I had it my way, I would have a time machine and put up a bunch of trail cameras in the Pleistocene, but I can't do that. So I am in the world of modeling. I'm working on a landscape reconstruction model to really get at these pollen sites within the climatic niche of pawpaw. So essentially, I reinvented the wheel, made another SDM for pawpaw, and took a bunch of pollen data from those sites, and I have begun doing this landscape reconstruction where we are using, and this is a very coarse model, we're going to iterate on this more to make it more complex, but we're using pine pollen to use as an indicator for these pine savanna habitats, grass pollen as an indicator for our grasslands and prairie systems, and then we're using alnus or alder pollen to get at the wet bottomlands forest, which is where we'd expect pawpaw to be. We can't use pawpaw pollen because it's insect pollinated, does not show up in the pollen record. And this model is trying to get at the biases that you find in your raw pollen data where pine and grass pollen sort of dominate. So it's parameterizing based on those pollen productivity estimates. And what we found thus far from these sites is that a lot of this area was very pine dominated, likely pine savanna, but the next steps for this is bringing canopy coverage into this to really understand if these are open canopy systems or closed canopy systems. And back to our megafauna, we've ran these maximum dispersal distance models. These are probability density curves of 1,000 dispersal events. So the simulated movement of megafauna being trained off of GPS colored movement, showing how far an animal can eat a seed, walk around a bunch, and then disperse it. This is a gill lab talk, so you're gonna see poop in the talk. That's just how it works in the gill lab. So what we see from this is what you would expect. The extinct Columbian mammoth is going to travel further in a day and move the seeds further than our largest living disperser, the black bear. And so from these preliminary results, what we understand thus far is that despite having a host of megafauna around, pawpaw may have been climatically constrained and constrained by the plant communities around it. to these coastal forests in the Pleistocene. And to prove that, we just got to do a lot more modeling. And with that, I would like to thank everyone that's helped me through this project. And I would also like to thank every pawpaw tree that I collected from. Thank you to Pawpaw for being a cool plant. Any questions in all of my? Yes.
3 sites you're using.
Those 3 sites were, and I'm using more. These are just the ones that I've done this model for. If I'm remembering correctly, it is Lake Waccamaw on the north, Camel Lake right there in the left one, and I believe in the middle there's either Lake Tulane or Lake Annie. Yeah.
You said that well, you're assuming mammoths travel distances the way elephants do, but black bears can travel tens of miles a day very easily. Do elephants do more than that?
Yes. Yeah. And also biased based on, the terrain they're traveling. Black bears are going to be in more closed canopy systems than elephants, being in these open systems. And also a bit based on their foraging behavior. I believe elephants are going to move around a lot more because they have to eat a lot more than the black bears.
Next, we have Kayla Guthrie, who will be presenting on assessing recovery from acid deposition in alpine lakes in central Norway.
Hi, everyone. I'm Kayla, and today I'll be talking about assessing recovery from acid deposition in high elevation lakes in central Norway. So, first off, why is acid deposition important and why do we care about the recovery? So, when I talk about acid deposition, I am primarily talking about the wet or the dry deposition of NOx and SOx. So, these are nitrogen oxide and sulfur oxide compounds. And for NOx, we're primarily focused on nitrate and ammonium. These are inorganic forms of nitrogen, and while they are readily available to the system, they can have quite dramatic impacts. SOx, I'll also be talking not a lot about, but it is sulfate deposition. And these compounds originally arise in the atmosphere from anthropogenic sources. So primarily through fossil fuel combustion in industrial processes, electricity generation, and transportation is also a big one. Everyone's probably heard of acid rain, I'm assuming. It was a huge problem in like the 70s and 80s, but it's not as much anymore. And so what does that mean for the environment? With acid deposition, there is a decrease in the pH as a system becomes more acidic. And there's also a decrease in the acid neutralizing capacity, or ANC. And acid neutralizing capacity is basically a system's ability to respond after acid inputs and to buffer that input and return to original state. With the terrestrial environment, there can be this mobilization of metals, specifically aluminum and mercury. This can be quite detrimental for living organisms. But with nitrogen deposition, there's also this altered nutrient balance. So with the inorganic nitrogen coming in, it can be good for organisms because that nitrogen is readily available for them to assimilate and use. However, there can also be nitrogen saturation, and too much nitrogen can be a bad thing, resulting in ultimately all of these things causing shifts in community structure. So who is there and the ability that they are able to perform in the system. So when I talk about recovery, I'm specifically talking about NOx and SOx emissions decreasing, leading to a decrease in acid deposition. All of this can be contributed to effective policy implementations. In the US, we had the Clean Air Act and all of its amendments. But for Norway specifically, I'm thinking about the Gothenburg 1999 protocol. And this was a protocol that targeted NOx and SOx emissions specifically, with emphasis on the international
transboundary pollution. So these emissions were primarily coming from Central Europe up into Norway. And what we would expect to see in a recovery phase from acid deposition is an increase in ANC and a decrease in these inorganic nitrogen compounds. In Norway, we see that there is this decreasing N and S deposition. And I do specifically want to point out the top right figure where there is that sharp decline in sulfur deposition. However, this study was only constrained to river and coastal surface waters, and the primary focus being there on fish populations. Salmon were heavily impacted by acid deposition, but now making a recovery. And the thing that I want to point out about the increasing total organic nitrogen is that while nitrogen is, a good thing for organisms to have, it's the form of nitrogen that is more of a concern for a system. Organic nitrogen isn't necessarily unavailable to organisms, but there are some microbial processes that need to take place in order to make that nitrogen into the more usable forms. And so where does that leave us for lakes? We do have this chemical recovery signature, but we're not really sure about the biological recovery signature in lake systems. And so why lakes? Lakes are sentinels of change, meaning that they serve as early warning systems for changes in the environment. And this is because they accumulate material from the water and the airshed. In these processes, they can do sedimentation, which is the accumulation in the sediment, and this serves as a record of change over time. So to understand how lakes in central Norway are changing, I wanted to use some modern chemistry and some paleolimnological methods to dissect. All right, so in Norway, I'm focused here around the Jostedalsbreen area. However, none of these lakes are glacially fed. They are all precipitation or groundwater fed. Halsavatna is a vegetated watershed. It is at the lowest elevation. And for these lakes, I do have some historical data. Halsavatna, I have water chemistry. Hornsavatna is a bare watershed. There is very little vegetation in this watershed at a higher elevation, and I have water chemistry and I have a boring record to compare it to. For Mishasvatnat, it is a bare watershed as well, some vegetation, but not a lot at the highest elevation. And I don't have water chemistry data to compare this one to, but I do have a previous core that I can compare to. And so for my methods for the water chemistry, I'm primarily looking at acid neutralizing capacity, total nitrogen, nitrate, ammonium, and comparing all of that to Clark 2003. For the sediment, I'll be looking at diatom assemblages. And for the diatoms, they are highly sensitive organisms, microscopic algae, and they respond a lot to nutrient and chemical inputs in their environment. I'll also be looking at nitrogen isotopes and lead-210 dating. For the water chemistry, the main thing that I want to point out here is that ANC increased from the 2003 to the 2025 sampling, suggesting that these systems are able to better resist acidic inputs. Nitrate and ammonium decreased. However, nitrate was below detection in my samples this year. For the sediment, and I should clarify, all of those water chemistry samples were taken from surface water. For the sediment, we went out and we cored at the deepest location of the lake. As you can see, it's a very thrilling process. And we took those cores back onto the shore, spliced them at half centimeter resolution. And then through that, I'm going to be looking at diatom assemblages, so who is there and how abundant they are. Also be looking at nitrogen isotopes to hopefully differentiate between sources of nitrogen. And then lead-210 dating just to get an accurate age of each resolution. So this is a beautiful image of my diatoms that I have so far. And as you can tell, there are lots of circles with lots of circles inside of them. And they are quite difficult to differentiate under normal microscopy. So it's taking some time, but it is important to differentiate species as each species has a different ecological niche and need that they fill. I'll also be getting some isotope analysis done, as well as sediment dating, and I don't have any data for that yet. But hopefully soon. And that's all I got.
I have a question on source emissions.
Mhm.
Is it seasonal or it's always from Central Europe?
I think it is seasonal, but mostly from Central Europe, and it does like transition towards like the right of the Scandinavians.
So I remember we were doing something and there was kind of air masses coming north towards Central Europe.
There are some air masses that come over from Russia, but I don't think it's as much of a problem compared to Central Europe, for Norway at least.
We're like drawing this Saharan dust transport over Atlantic and then it would circle back to Europe.
Mm. Not as
Just simply
familiar
a
with that,
tracer of
but
Saharan dust in the spring.
yeah.
Thank you.
Regarding the more recent increases in nitrogen, I'm curious if you're planning to look at some of the climate-related events such as that changes in precipitation, temperature, and ice-free days, which will all influence the internal cycling of nitrogen.
Yeah, I haven't considered looking at some of the more climate signatures of recent. I do have some in-lake temperature data, and this upcoming year I'll also be deploying more temperature sensors. But in terms of like the atmospheric temperature, not as concerned about. But
Very exciting.
thank you.
All right, next up we have Caitlin Johnson, who will be talking about calibrating isotopic analysis of trachycardium shell material as a proxy for ENSO behavior in Peru. Thank you so much for this.
Okay, hi everybody. So yes, I'm talking about isotopic analysis of mollusk shells. The idea here is that we're calibrating a new method of using mollusks off the coast of Peru to track and document changes in El Nino southern oscillation. And I'll be using modern shells and archaeological shells to try to see the difference between modern and past ENSO behavior. So first I wanted to do a little bit of an overview about El Nino Southern Oscillation. So broadly, it is a change in climate reversal across the Pacific Ocean. The El Nino component of this is a change in sea surface temperature across the Pacific. And this is largely driven by a phenomenon called the Southern Oscillation, which is a pressure differential across the Pacific Ocean. So on the eastern side of the, on the eastern side of the Pacific, we have a high pressure zone, and on the western we have a low pressure zone, and this drives trade winds across the Pacific, and with it, it drags sea surface water, moving a blanket of warm water across the Pacific towards the west. And this leaves along the coast of Peru the opportunity for upwelling to bring cold, deep, nutrient-rich water up to the surface, and we get colder sea surface temperatures there. So this is our normal conditions. So every 2 to 7 years, approximately, these temperatures reverse, and we get what's called El Nino or La Nina, and there's other flavors of it as well, but I'll just talk about these two briefly. So during La Nina, these trade winds strengthen, and we move more of that warm water westward, and what we see is that we have more cold water as the opportunity for upwelling increases. And we get colder sea surface temperatures and drier conditions along the coast of Peru. During El Nino, the opposite happens, and so these trade winds weaken, and we allow westerly winds to move in and move that warm water back towards the coast. And what we get is warmer sea surface temperatures, decreased upwelling, and overall wetter conditions along the coast of Peru. So in Peru, there's a lot of the typical paleoclimate records we would use to study El Nino are not present. So we don't have corals. We don't have a lot of ice cores. And so one of the ways that we can look at El Nino is by using the archaeological record. And what's more common on the coast of Peru in the archaeological record than shells? So this is a drawing I have done for you of Trachycardium procerum. This is one of the shells that lives off the coast of Peru. It lives about 1 to 3 years, and it deposits shell material about once or twice a day. So it makes it a really high resolution record of a pretty short period of time. And unlike a lot of other cockles or shells on the coast, they actually will grow through El Nino conditions. And so other ones will die off if the temperature gets too high or too cold. And what we see here is that on the surface of the shell, and I've indicated this by these like darker bands in the growth rings, are shocks in temperature. So that's when the temperature gets too high, but they'll grow through it. So that's one way we can look at it, but I wanted to see if there were any differences in the actual composition of the shell that could tell us about El Nino more specifically. So before I get into the methods there, I want to talk a little bit about my sample collection. So these shells come from Nuevo Chimbote, Peru, at a site called Fly El Dorado. And we live collected these 10 shells with the help of local fishermen. And then I actually took these back to my hotel room and hand shucked them in my sink. I have that video if you're interested. Just come find me. It's pretty funny. And then I traveled to the equally tropical Iowa State University, where I sampled my isotopes. So I collected samples from 2 modern shells and 2 mid-Holocene shells. Those mid-Holocene shells were from the existing collection, and they're actually from Oster Collecting Station, which Emily talked about earlier. So, but I won't talk about those today because I do not have time. But the 2 modern shells I sampled from the hinge, so at the top of the shell, all the way down to the bottom in 1 millimeter increments. And in total, I collected about 600 samples across the 4 shells, and then I ran carbon and oxygen isotopes. So in addition to those 2 shells that I sampled, which are 9B and 10B at the bottom of this slide, I also have 6 additional shells that were courtesy of Dr. Alan Wanamaker at Iowa State University. And I've labeled them here according to their primary ENSO conditions. So EN1 and EN2 grew through a really strong El Nino in 2015. The neutral shells, I'm calling them neutral in that not more than 50% of its growth was spent in any one condition. So you'll see here that N1 and N2 and my new shells all grew through both an El Nino and a La Nina episode. So their data is pretty interesting. We'll get into that here. So I mentioned I'm doing carbon and oxygen. So carbon is a ratio, or the delta carbon 13 value that I'm looking at is a ratio between the heavier carbon 13 and the lighter carbon 12. And the idea here is that I can absolutely go into this in questions if you're interested, but the more positive the carbon 13 value, the less upwelling we have, and that's a signature of El Nino. The opposite is true. So the more negative that value is, the less or the more upwelling we have, and that's a signal of La Nina. So then we also have, I sampled delta oxygen 18 values, and that's the ratio between the heavier 18 and the lighter 16. A more positive oxygen value is a colder sea surface temperature, which is common during La Nina, and a more negative oxygen value is a sign of warmer sea surface temperatures, which is common during El Nino. So you can already start to imagine if I were to plot these 2 lines, X, Y on a graph, you can start to see where these shells might start to appear. So our El Nino shells, we would expect them to end up down in the bottom right-hand corner. Our La Nina shells, we might expect them up in the upper left-hand corner, and our neutral shells should end up somewhere in the middle. And this is exactly what we see. So this first one I'm showing here is our El Nino shells. I separated them out just so you can see them a little bit better, but they are really beautifully separating, as you can see here, into the bottom right-hand corner, which is really exciting. And that is a pretty good indicator that based on just this isotope values, and I should note here that these values here, every dot is one isotope or one isotope value, so a carbon and oxygen. Those circles are 95% confidence ellipses. So that's where the majority of the data falls. And this is the entire record. So I took the entire shell record. It's not set in time. I haven't pulled out just El Nino episodes. This is all of the data. So you can imagine if I were to go through and separate all the data out, it would separate even further. And I have done that, and you can see my thesis defense in June if you're interested in that part. So then our La Nina shells do separate out not as nicely as the El Nino ones, and this is likely because the La Nina event that was reported in these shells was much less intense than the El Nino event, so it's not moving as further up towards the left. We also see a pretty significant overlap between La Nina and neutral shells, but the neutral shells are still occupying that middle zone. And in order to show the neutral and how this is actually shaking out, this is the addition of my new 9B and 10B. And you can see that it is overlapping really nicely with that neutral zone, which is pretty promising. I think the difference here is that the neutral shells are, because they're a total record, it's obscuring some of those individual events. And so the strength of the individual events within the records might adjust how big or small or the orientation of the ellipse. And then just for the sake of the data, I guess, I've also done the mean value similarity between these shells. So for carbon and oxygen, carbon's over here on the left and oxygen is on the right. You can see here the dots represent the mean values. The error bars are the 95% confidence interval, or plus or minus about 2 standard deviation. And you can see that the oxygen values for both carbon and oxygen, or sorry, the carbon and oxygen values for the El Nino shells are really beautifully separated from the other ones. And the idea is that if the intervals do not overlap, they're statistically different. So this is another pretty promising result for that. So just to summarize, how well does Trachycardia and Procerum actually record El Nino events? So I think it's pretty clear that El Nino shells are the most identifiable out of any of these events. This might be due to the intensity of the El Nino event, but this will come out whenever I align it more in time. The neutral or the La Nina shells, they do separate out, but it's less significant, and that's likely due to that intensity that I was talking about. And then those neutral shells, so those the N1 and N2, as well as our 9B and 10B, my new 2025 shells, I think are masking some of that individual variability. So the next stage of this, and I have done this, is to align these shells in time so that you can actually compare it to the sea surface temperatures and the El Nino, the recorded record, so the actual documented El Nino events, and compare the isotope values across these different events. And those results are really interesting as well. And then the last component of this project is to look at those Holocene isotope values, and there's a lot to get into for that, which is why I've excluded it from today's presentation. So then I just wanted to thank the Sturgis Family Foundation Fund, as well as the Iowa State Isotope Lab, my thesis committee, my fieldwork team from Peru, and a special thank to John Flores, who was the person who collected my shells for me, so I did not have to scuba dive. And yeah, I would love to take questions.
And you said they were living organisms that were collected.
Yes.
And they lived 1 or 2 or 2 or 3 years or something like that.
Yes.
But they would have all been the same age roughly, right? Why would some of them be El Nino and some not?
Because so when I labeled the shells, I labeled it based on what type of event it was primarily growing through. So for example, my 9B and 10B shells, they're 2.5 years old. And a portion of that was spent in El Nino, a portion was spent in La Nina, a portion of that was spent in neutral. So I labeled them neutral because they're not spending more than their record.
When were they collected? Were they all collected at the same time?
Oh, yes. Sorry. Yeah, they were all collected in July and they're.
But in the same year?
Yes.
No, once. You've got the 17 collections.
Oh, I thought you were talking about the modern ones. Yes. So the
modern ones, but there are what, 4 modern collections?
I was just trying to.
Yeah.
That
So
would answer George's question.
Yeah. You were able to know whether they were at El Nino time or not.
yes.
It's got the harvest date there.
Yeah.
Thank you.
Where did the cursor go? So Cicely is unable to be with us here today, but if you're interested in her work doing outreach in the Yukon, you should come find her at another time and talk to her about it. But instead, we will just skip on to the next talk and we will hear from Matilda again. And we are. And she will be talking to us about estimating spatial variation in snowmelt and snowpack on the Juneau Icefield in Alaska.
Thank you. Good to see you again. I am all that stands between you and a break, so please
stay tuned. I've titled this talk Estimating Spatial Variation of Snowmelt to Enhance Understanding of Meltwater Input and Storage in the Snowpack at Taku Glacier on the Juneau Ice Field in Alaska. But that's quite a mouthful, so I've put it into where is the water? That's the big question of today. And this research is investigating surface elevation changes in North Basin, which is a little part of Taku Glacier, which is a part of the Juneau Ice Field in Alaska. And talking about this place, I would like to start with saying that this research takes place on the unceded land of the Taku River Tlingit First Nation, and I would like to thank them for their long-standing stewardship, deep relationship with this land, and for how they continue to shape and sustain it today. Moreover, I would very like to extend a big thank you to the Dan and Betty Churchill Exploration Fund for financial support to get me into the field and learning these methods, learning how to teach and learning how to do research. I would like to thank Wyatt, Scott, and Seth for being part of this science and research collaboration, for Kaylee, Renee, Cicely, Dylan, and Wyatt for emotional support. This was a rough season for me. And to all the JERC students, faculty, and staff for teaching me how to teach, because I will talk to you about all the research in just a minute. But one thing that really stood out to me as well was for me being in this, taking part in this field season while field education was taking place, and that I could be the bridge between the research that we do to these students. And one of the things I talked a lot about was how we in North Basin investigated what was going on through a lot of different methods, which is what my talk today also will be about. But let's zoom out and get the big picture. I said, where's the water? Today we've heard a lot about different places, different things. Yesterday I listened to Amber's poster about the NAO, talking about what's happening in the atmosphere. Today I will talk about happenings in the cryosphere. We listened to we listened to Elizabeth talking about erosional features and archaeological sites. And we listened to Morgan about coastal birds and the biosphere. All these different researches, both connected through water, but unfortunately also through our anthropogenic influences and climate change, which unite us here as the Institute. So today I would like to see how water and climate change is affecting the cryosphere. Zooming in a little bit, the big question of like what's happening is that we're seeing accelerated glacial melt today, and in the next coming decades we're expecting peak glacial melt and input, and unfortunately a lot less glaciers in the future. But this peak melt, this input of water, where does it go in the glacial system? We do not know. Will it be stored and buffered in the snowpack? Will it run straight through the system and directly influence sea level rise projections? And does it lubricate the glaciers? Do they flow faster? Does all this water change from these dry conditions to wet conditions, so the research methods that we so far have made don't work anymore? These are all questions about water in a changing climate. So why do we want to study Alaska? Why is this a great place to be? There's this study by Semp et al. That Renee also talked about, where we see the global glacier mass change from 1961 to 2016. That's over 55 years, where a third of it stems from Alaska, and this is excluding the polar ice sheets again, which makes this a very big region of change. Moreover, this is a temperate ice field at the pressure melting point, which might be a good model for what we might experience migrating further towards the poles. It has high melt and high precipitation, meaning there's a lot of water in and coming into the system. And at the Juneau Ice Field, there's the Juneau Ice Field Research Program, which has a long history of research with rich data sets of tracking change, as well as close proximity to humans, which making access to the ice field and monitoring more cheaper and easier. So let's go there. The Juneau Ice Field is the second biggest ice field in Alaska. And to the right here, we see the Taku Glacier. And up here in the corner, we see North Basin. And North Basin is this little area on Taku Glacier.
surrounded partly by nunataks, approximately 500 by 1,000 meters. And across North Basin, what I did during the field station was put up 8 ablation stakes. You might ask, what is an ablation stake? An ablation stake is a stick we put into the snow and we measure the snow surface, and then we resurvey it through time, maybe on day 3 and day 5, and we can see changes and we can measure snow melt. So I skied out or got help on a snowmobile and put them across North Basin, and they were all made of bamboo. This is ground truthing with a very simple tool. And what I found was we saw some spatial variation. You see all of these plots are not the same. And as time progresses, if we go to day 8, we see that the max, the minimum, the range, and the standard deviation, the variation within the data set increases. Therefore, we can say a little bit about it is melting, but we still don't know where the water goes. And to answer that question, my ablation stakes cannot stand alone. We need other data sets. One of them we also collected was a GNSS measurement, where we saw on the first day where our ablation stake was, and then we measured it on the last day and saw that it was flowing on the glacier for 5 meters over 8 days. But other research also takes place on the Juneau ice field. One of them is an excessive amount of ground penetrating radar, both in the near surface, looking at the snowpack, the firn, but also long transects of deep radar, looking at where is the bed, how thick is the ice, is there water at the bed? And these are more, this is above the bamboo stick, but we'll get to that. We also have a new tool called the terrestrial radar interferometry, which can get very, very high spatial and temporal resolution changes in the snowpack. We have a long, long record of snow pit and glacier mass balance estimates from these. That's also been put into models. And while I was there as well, we have unmanned aerial vehicle LiDAR surveys used to make high-resolution digital elevation models, where I help with the ground truthing here as well. Because ground truthing is important, because we can have all these high-resolution data sets, but what if they don't agree? Who then holds the right? Maybe the ground truth that my ablation stakes could provide, could help. So by combining all of these together, we can start to understand the surface elevation changes in North Basin and maybe start to disentangle what stems from melting, which would be loss of ice due to temperature changes, what would be due to either uplift or subsidence, which could be caused by the glacial lake under the North Basin draining and suddenly a change in the surface, and what would be generally just due to flow and compaction of the ice. And by integrating multiple data sets, where we both have the high complex and the ground truth through the ablation stakes, we can better understand these diverse drivers of elevation change in North Basin. So what I would like to leave you with today is that ground truth is important, and that collaborative research can answer these complex questions about our future. Thank you. Thank you.
All right, we're going to go ahead and begin our next session.
Except here.
All right. All right, first up, we have Thomas Brindle, and they will be presenting changing susceptibility of dissolved organic carbon to UV radiation following lake browning in West Greenland.
Good morning. Thank you so much. I'm excited to be presenting today about part of my research in West Greenland as part of the SANA NRT, specifically about a experimental setup that I have ongoing investigating dissolved organic carbon and its susceptibility to photodegradation and photobleaching. So, first up, lake browning. This is a phenomenon currently ongoing in West Greenland as a result of an autumn 2022 season of anomalous heat and anomalous precipitation. These two extreme events that struck the region at the same time as a result of 9 individual atmospheric rivers coming up to this area of Greenland, marked with the star. That is the Kangerlussuaq area of West Greenland. Imported large amounts of both heat and moisture to the region that is typically an arid tundra environment. This fell as rain in a manner unusual for the region, which resulted in widespread lake browning that was abrupt, broad scale, and coherent across the landscape. So previous differences in the lake structures, differences in where the lakes were on the landscape, differences in trophic state, differences in thermal structure, all of the things that make the lakes distinct from each other had very little bearing on how they were impacted by this event. The lakes that I study, I want to point out, as I do work in Greenland, are near the Greenlandic ice sheet, but they are not hydrologically connected to the Greenland ice sheet. These are principally fed by meltwater, by groundwater, and by precipitation. So, when there is unseasonable precipitation in these lakes, that impacts their water balance rather abruptly. When limnologists talk about browning, it is quite descriptive. Blue and brown are technical terms to describe the state of a lake on the color and nutrient paradigm, but it is also a descriptive of the color of the lake. These two pictures down in the bottom were taken about 8 months apart. This is a fairly significant change in the lakes. If you showed me those pictures without the context and asked how far apart those pictures were taken, my estimate would be in decades. This happened over the course of less than a year. They browned regardless of previous watershed characteristics, and this has widespread impacts on the lakes themselves, on their function in the carbon cycle, on their function on the landscape, and on their ecosystem themselves. This phenomenon was reported on broadly by the Saros 2025 publication in Proceedings of the National Academies of Sciences, describing a broad manner of changes that covered how the lakes are set up, who lives in the lakes, the diversity of the bacterial communities, the lake's ability to process carbon, and whether they are a sink or source during the summer. Everything is impacted by this lake state. Browning in these lakes is principally driven by iron and dissolved organic carbon. Iron is principally derived from the area around the watershed of the landscape. This is a region with fairly iron-rich soils. And dissolved organic carbon can either originate inside the lake, or autochthonously, or outside the lake, or allochthonously. And those DOC pools will have different attributes. They will have different positions, I guess, in the or responses, more aptly, to processing. So the areas of interest specifically that I'm looking at are lakes in the inland area and near the ice sheet. Again, not hydrologically connected to the ice sheet. The inland areas, they typically are wider according to their depth, and they are typically in areas with warmer temperatures, calmer winds, different climatic influences on how these lakes would otherwise function or establish. Ice sheet lakes, their climate is very strongly influenced by proximity to the Greenlandic ice sheet. They are not, again, hydrologically connected, but they do have typically more wind, and it's often colder, and the slopes of the lakes are often deeper, which is another factor that influences how lakes may be different. So despite all of the various differences in these lakes, they're separated by a span of a few miles. They all reacted similarly. And I'm interested in how and why. So when I'm looking at dissolved organic carbon, I'm looking specifically at how this is going to react in the future. Dissolved organic carbon is one of the principal components of browning, and that means that when it breaks down, that influences how the lakes are brown in the future. That color, the color axis on color nutrient paradigm, it relies on things like how complex the dissolved organic carbon is, how long the dissolved organic carbon is, how easily broken down the dissolved organic carbon is. So DOC is part of a broader matrix of dissolved organic matter that can bring into bring into play all sorts of elements that aren't carbon, but I'm principally interested in the carbon backbone of it. So it's potentially susceptible to decay both in the length of it. When you break that down, that's called photodecay. And in the matrix complexity, when you break down that aromaticity of those organic rings, then you will lose some of the absorbance of brown light that drives the browning then in the lake itself. That's photodegradation and photobleaching respectively, and they have different chemical markers in the spectra of these compounds. And just to kind of point this out, this is from that Soros 2025 paper that I mentioned. These quality metrics do respond very strongly to browning. SUVA 254 is UV absorption at 254 nanometers weighted to relative DOC concentration in these pools. It is reflective of aromaticity in the chemical structure of the in-lake DOC and compounds created outside of the lake, so that's those allochthonous compounds that would have been swept in during the event, tend to be more aromatic than in-lake compounds, and that is reflected in our observations over the course of the past decade or so. The character of SUVA in the lakes, of how these compounds spectrally respond, changed abruptly in 2022 to indicate that it's probably DOC pools that are more allochthonous, more originating outside of the lake. Similarly, spectral slope is a little bit of a different measure looking at the difference in absorption between two different wavelengths, and that tells us how long these carbon chains are. They're indicative of the allochthonous compounds, which tend to be longer than autochthonous. In this case, while SUVA goes up when you become allochthonous, spectral slope goes down. So in the time sense, there was a little bit broader of a diversity of spectral slope characteristics prior. So it doesn't look visually as distinct, but I do promise those are statistically distinct from each other before and after the browning event, the onset of browning in these lakes. Spectral data indicates a shift from the previous low color, high DOC system. That is noteworthy for these systems. They did have a lot of dissolved organic carbon, but that dissolved organic carbon was typically very thoroughly bleached. So in order to do this, I've got an experimental design going on. I'm gonna kind of move through this rapidly so that I can show you some results as well. But I draw some samples from the epilimnion. That's the top layer of 3 lakes in West Greenland, representative of different watershed and vegetation characteristics. Some are frozen, some are moved into a particular UV penetrable form of plastic bag, and then others are put in that plastic bag and then wrapped in tinfoil so that they are protected from the light and placed outside for a week so that they can be bombarded by UV, and I will be able to compare before that UV exposure and after that UV exposure from Greenland's 24 hours of daylight in the summer. This is what it looks like in the field. We've got various things wrapped. We've got some flask controls to make sure that I can that the carbon that is in the bags themselves isn't leaching into the experiment itself. And I've got my light, I've got my dark. Let's take a look at some results. Photodegradation. This is, again, proxy for spectral slope. This is how long these carbon chains are. There is strong evidence of increased susceptibility to photodegradation in post-disturbance DOC. I'm comparing this, I should probably have mentioned this long before, but I'm basing this off of work done by Dr. Rachel Fowler of the School of Biology and Ecology, who published it in 2018. So I have data from before the browning and after the browning. You'll notice before the browning, very little difference between dark and light. After the browning, we have that large rise. That's true in both SS2 and SS901. And when it comes to photo bleaching, we have that SUVA 254 susceptibility to bleaching may impact the light color. We get similar trends before and after the browning event in SS2. So we have evidence of a change in the DOC pool, but the DOC pool was not uniformly unresponsive to UV light in the past. Thank you. SS901, side note, does not show that in the 2025 samples, but that may be due to some sampling complications that I won't go into here, but there's reason to maybe call that data into a little bit of question due to transportation difficulties. Thank you very much. I know that I kind of threw a lot at you in the past 10 minutes, but I appreciate your attention, and I just want to extend my thanks to a number of people and institutions, including those who have previously funded my work and who under whose auspices I continue to work. Thank you very much.
We have time for.
Yeah, sorry.
You mentioned that these things you were looking at were hydrologically connected. What do you mean by that? Because unless you misspoke, I believe I heard you said that they were fed by water from it. So what do you mean by hydrologically disconnected?
Yes, sorry, I should have clarified. Thank you very much. When I referenced meltwater, I meant snowmelt. So there is not a direct line of water melting off of a glacier and then flowing into these lakes. There are many lakes in the region that do have that characteristic, and they responded very differently to both this phenomenon and also are generally structured very differently. So the meltwater in question, when I mentioned it was melt precipitation in groundwater, that's snowmelt, not ice sheet melt. So there is no direct hydrological connection between these lakes and the glacial system. Thank you very much.
All right. Next up, we have Trisha Hall Collins, and they will be presenting Scandinavian ice sheet behavior during the last deglaciation and late glacial climate reversal.
Okay, morning all. I'm going to be walking you through a component of my dissertation. This started a couple of years ago when I traveled to southwestern Norway to Lyse Fjord. And the idea of going here was really rooted in, it's in the North Atlantic region, which is interesting for several of the questions we're trying to answer. And one of the unique things about this field site is that basically within this fjord, there's an entire flow line's worth of glacial features to take advantage of. So that's kind of rare to find. In this photo here, you'll see the fjord looking out toward the mouth from about a midpoint. And during the LGM, this view is entirely filled with ice. From the waterline up, those highland plateaus are about 500 meters tall. So that was all full of ice. And during the deglaciation, as the ice retreated back, it was depositing erratic boulders like those that you see in the foreground here. So we're really trying to test several hypotheses that are being proposed to explain differences in different paleoclimate records. An example of what I mean by that can be seen in the Greenland and Antarctic temperature records. So you'll see during the early part of the deglaciation, Heinrich Stadial 1, Antarctica is showing a warming trend, and that's not readily apparent in the Greenland record on top there of the graph. But then during the Bowling Alley Route and ACR time, both of these actually do show a cooling trend, but those average temperatures of Greenland are quite a bit higher than during Heinrich Stadial 1. And then during the Younger Dryas, there is a warming trend seen in both, but those average temperatures in Greenland are quite a bit lower than during the ACR and Bowling Alley Route time. A couple of hypotheses that are out there on the table include the bipolar seesaw hypothesis. The consequence of this being the northern hemisphere, for instance, would have to warm at the expense of the southern hemisphere via oceanic heat transport. Another hypothesis on the table would be enhanced seasonality. And this really gets at the idea of, especially related to Greenland, that perhaps really cold winters have a heavy influence on that climate signal. There's evidence for 26 to 28 degrees C colder winters in Greenland during periods like Heinrich Stadial 1. And as a bit of a spoiler, my data do align most closely with that Antarctic signal. I targeted two types of glacial deposits in this work. On the left side of your screen, you'll see erratic boulders. These are perched directly on bedrock or within fine till, just like on the title slide. One thing you can do with these is because they're most typically associated with a disintegrating and retreating ice front, is you can actually follow a flow line up my fjord, for instance, and track the rate of retreat. The right-hand side shows a moraine from my field area with boulders embedded in it. And these are formed when that ice front stays at one spot for at least some time and has ample sediment supply to build up that ridge as it deposits all of that sediment. So in the lower right there, you'll see an approximation of the Scandinavian ice sheet during the last glacial maximum. It was stretched all the way out to the continental shelf. And by 16,500 years ago, it had retreated all the way back to Lisa Fjord, which is shown in the yellow polygon on that figure there. And what I'm going to do is walk you through the evolution of the Lisa Fjord Glacier and the deglaciation by going to each of these colored dots. They're clusters of samples that I collected. So I'll walk you through that chronology that way. I'm going to start with the yellow cluster of dots here on a bedrock hill called Ubrin. So Ubrin is about 400 meters tall, and it has erratic boulders deposited all along it. And as the ice retreated and that surface lowered, it exposed about a 400 to 500 meter tall highland plateau there, where you see the green dot showing more erratic boulders. And these positions are all outboard of the really well constrained late glacial ice position, which is at about 12.8 thousand years ago. So Ubrin averaging 16,500 for that deposition. Then you'll see the plateau that's a slightly younger age population. So significant retreat laterally, yes, but I'll point out at 16.5 on about a 90 meter tall bedrock hill near that late glacial position is the same age as Ubrin. And so this was really rapid ice surface lowering. Now moving to the northern end of that plateau, there's a complex of moraines. And this is going to signify a more stable period of ice sheet position. So while all of that retreat we saw on Ubrin and the Highland Plateau, that's Heinrich Stadial 1, now we're going to start entering the Bowling Alley Route and ACR time period. In green, you'll see a few of those erratic boulders still in view. And the first moraine that I'm going to talk about in this complex is a rock moraine with a photo of it here in Katie for scale. And it kicked off that Bowling Alley Route ACR time at about 15.1 thousand years for deposition, with the next moraine being deposited at 14.8, 14,000, 13.5, and the youngest moraine being deposited at 12.7 thousand years. So keeping that age in mind for just a moment, we're going to jump to that midpoint. So this is where I was on the title slide. And you'll see that age is the same. So we're talking about massive retreat following the ACR time during the Younger Dryas from at least the northern end of the plateau to at least the midpoint of the fjord, all within the era of the method. So this is during Younger Dryas, and you'll see on the lower right a different shot from that site on it was a combo rainy and buggy day. So up at the head of the fjord, there's a collection of moraines that are effectively plastered against a steep bedrock cliff, making for a bit more, complexity geologically. I think this area is prone to rockfall, and it's so steep that some boulders from higher moraines can even roll down to lower ones. But with that said, I do see two distinct age populations, 10.8 and 12,600 years ago. What this helps us see is that from that midpoint, the glacier had retreated back to the head of the fjord within just a couple hundred years. Okay, so to start to put this in a more global context, I've plotted my chronology in the black dots. On the x-axis is time getting older to the right, with distance on the left y-axis. And what you can see is during Heinrich Stadial 1, I've indicated Ubrin there for you as a reference. The Lisa Fjord Glacier retreated at least 70 kilometers. That's certainly a minimum estimate. And then just prior to and during the Bowling Alley Route ACR time, the Lisa Fjord Glacier readvanced and stabilized, depositing moraines in an oscillating fashion throughout that time, with then final retreat out of the fjord during the Younger Dryas. On the right-hand y-axis is temperature, and this is associated with those green points on this plot. That's a glacier temperature record from New Zealand. And one thing to know about glacier systems is they are primarily sensitive to summertime temperature. So we're effectively looking at the same climate signal here, even though one is distance, one is temperature. But you'll see the curves look the same. And so the Lisa Fjord system is behaving the same way as a glacier record from the Southern Hemisphere. So what that tells us is that because the hemispheres are behaving the same in terms of this glacier, in terms of glacier records, that this doesn't really fit the bipolar seesaw hypothesis. And given that my record resembles the Antarctic signal, we might need to explore further that it's compatible with the enhanced seasonality hypothesis as a potential explanation for some of the disconnect between different paleoclimate records. And so with that, I'm happy to take any questions.
How could we know temperature during the 12,700 years ago from Greenland?
From Greenland. So you're talking younger dryas time?
Yeah.
So my understanding is you have lateral moraine temperature estimates from Greenland, as well as ice core estimates.
Next up, we have Kaylee Manello, and they will be presenting on evolution of temperate fern under melt. And so thanks so much.
Well, hello. I am delighted to share with you some of our most recent work contributing to this understanding of evolution of temperate fern in Southeast Alaska. And first, I want to draw you all into the place that we think about a lot and that is near and dear to my heart. So this is just at sunset looking southwest across Taku Klan Sit, which is one of the largest temperate glaciers in North America. And it spans about 5 kilometers across from the viewpoint to the next mountains. And Taku Klan Sit is one of the main outlet glaciers of the southern portion of the Juneau ice field. And the Juneau ice field is located on Tlingit Anai, which is on the traditional and unceded territories of the Ak Klan. And it's a really incredible place to be and experience. And so, as we've heard from several presentations thus far, glaciers in Alaska contribute to sea level rise, and they do so in a big way. There is both a high rate of mass loss, and this is indicated or demonstrated by the figure on the right here that's modified from Duciant and others published last year, where we have time on the x-axis and then mass change and sea level rise equivalent on the y-axis. The bold line here is the global mean, excluding the polar ice sheets, and the purple line that I've highlighted here is contributions from Alaska, demonstrating this high rate of mass loss compared to other glaciarized regions in the world. So glaciers in Alaska have both large historical and future projected contributions to sea level rise, so we're really interested in this area. And my title here mentions fern. We've heard a lot of talks, and this is not the plant fern. This is fern that we define as snow that has survived the melt season. And this snow then actively densifies into glacier ice with subsequent snowfall. And so the schematic on the right is showing how we have very low density snow, big crystals that get metamorphized into fern that's becoming more dense as we reach the incompressible density of glacier ice. This is important because this is an ice mass input. So the fern that sticks around eventually becomes glacier ice. And this, because it is porous, may buffer contributions to sea level rise from surface melt. The thing is, we don't know how much fern there is here and how that's varied through time. And so what our goal here is to quantify fern volume on the Juneau ice field between 2012 and 2025. Several folks have introduced you to where we are in the world, but I'll just remind you that this is a temperate ice field, so it's existing at pressure melting point throughout. And importantly, Taku Kwan Sit transitioned from advancing to retreating sometime in the mid-2010s, so within our study period. I've zoomed in this Landsat image on the left, or sorry, Landsat on the left, and this is the southern portion of the ice field with the blue area, or sorry, the purple area is where we have surveyed. And so in order to study fern, this is something that is beneath many meters of snow. We use a method called ground penetrating radar, which is a non-destructive method that we can acquire vast spatial and temporal measurements through time to see what is in the subsurface. And so we've repeated this glacier centerline transect from low to high elevation in multiple years during our study period. So what we do with this information is that we identify the horizons within our radargram. And this is to determine how much snow accumulation we have, where that boundary is with fern, and then where our glacier and fern boundary is as well. What this does for us is give us an ability to quantify fern thickness spatially and temporally. So I'm presenting to you today some preliminary results on fern thickness and volume, and I'll introduce you to the plots that we'll look at and build through the rest of the presentation. So on the left here, this is zoomed into that purple transect that I showed you before, where the colors represent fern thickness in meters, where low fern thickness is in red, and then we have cooler colors representing greater fern thickness. At the top, I have 100%, so all of the further plots that I'll show you are percent fern volume relative to this first year. So relative to itself, 100% fern volume here. So our next survey year that we've analyzed so far is 2021, which is 9 years later. What we notice looking at our center line here is a lot more prevalence of red and far less prevalence of blue and cooler colors, indicating a great loss in this fern thickness, such that this represents only 43% of the volume of fern that was present 9 years prior. To put this in physical context for you, the mean fern thickness value that we had in 2012 was around 10 meters. And 10 meters, we can consider approximately from the floor to the top of the ceiling here, which is a lot. And then in 2021, that number was closer to 4 meters. And that takes us, we measured yesterday, to the top of these silver ducks. So a pretty drastic change. And so this leaves me with feelings of sadness, but I'm delighted to continue to have a little bit of hope in that the 2 years later, we see a recovery in some of this fern thickness and volume. We have a little bit of a change in how that's distributed, but we've recovered up to 75% of the fern volume that we observed in 2012. This is further shown in 2024, the next year, and then we hover around 76% from last summer. We can think about how and why we're seeing this change that we maybe didn't expect in a glacier system that we're saying is retreating in a climate that is progressively warming. We can think about that with this long-term record from the Juneau Icefield Research Program and compiled by the USGS, showing winter balance that we're using as a sort of proxy for precipitation in this area that we don't have precipitation gauges. And so what this is showing, I have the year from 2005 to 2025 on the x-axis, and then winter balance in meters water equivalent on the y-axis, where yellow vertical bars here represent years that we have radar data. And above the dotted line is above average winter accumulation, so we have more snow. But below that is less snow than average. And what we see from this initial year in 2021 with that drastic drop in fern thickness to 2012 to 2021 is far less snow than average for a sustained period of time. And then we see 3 years of above average snow, which is really exciting. And I think You'll notice then on top of that, I've plotted the mean fern thickness values in these black dots, and I find interesting how similar the shape is, especially from 2021 onward, to that resembles just 2 years prior. We can't think about glaciers with just snow. We also have to think about melt. And another way that we can look at this is using the summer balance, where in a similar fashion, we have year on the x-axis and summer balance on the y-axis, where the horizontal dotted line is representing the mean over 30 years. And we see less melt preceding our high 2012 values, and then more melt between 2012 and 2021, and a little bit of variability in the later years. To summarize, what we observe here is a greater than 50% decrease in fern volume between our initial and second year of analyzed data, which is following a period of below average snow accumulation and above average melt. We also see a recovery of fern volume to near 2012 levels after around 3 years of above average snow accumulation. The implications of this is that the Juneau ice field is highly susceptible likely to variability in snow accumulation and melt. Now, this isn't necessarily new news when you think about a glacier. We are always balancing accumulation and melt. But what's interesting is that these periods of influence appear to be on the sub-decadal scale within very few years preceding those fern volume measurements. This is potentially indicating a short residence time of fern, and putting this place on sort of the precipice of the balance of few years of really good snow accumulation can recover in the system. But if we also then have a period of sustained loss, we're in a bit of trouble. So I want to acknowledge that this work is happened over many, many years with so much time and effort. So thank you to everyone involved here, and I'm happy to take any questions.
Thank you so much. What's the rate of loss of fern to glacial ice? How much of each year's fern do you expect to have compacted into glacial ice by the next year?
That is a great question. That is something that that's like an active area of research, which is how quickly the fern is densifying into glacier ice. So stay tuned, and maybe I'll share that next year or the following. Thanks so much. Nestor, you had a question?
Yes, I was just wondering for the percentage figures that you gave, what is that averaging over? Is it the depth, or is it some kind of spatial averaging volume?
Yeah, that's a great question. So this is averaged over, I've taken, excuse this slide here. So you'll notice these are slightly different like lengths of surveys, and I've constrained the actual analysis here to the smallest survey extent, which is 2021. And so the data are interpolated within that space to 1 kilometer on either side of the center line to calculate volume. And so I guess the percentage doesn't necessarily represent an average, but I hope that answers your question. Thanks so much.
Next up, we have Anna Truba, and they will be presenting on analysis of the December 18th, 2023 extratropical cyclone.
Okay. Hello, everyone. So today I'm going to talk to you about the beginnings of my dissertation work, which is part of a larger NSF project called STORM, data-driven approaches to secure electrical grids. In recent years, there have been a number of strong cold season cyclones that have brought heavy rain and high wind gusts to Maine. These storms have led to significant damage, including flood damage and electrical outages across the state. Among these storms is one that occurred on December 18th of 2023, which was a sou'easter. My dissertation aims to evaluate case studies of recent impactful storms and develop a historical storm climatology to better inform electrical grid resiliency and emergency management. Little bit of background. What are extratropical cyclones, and specifically what are cold season extratropical cyclones? They are mid-latitude storm systems, and so these are storms centered around an area of low pressure in the mid-latitudes, and they tend to intensify with a stronger jet stream. One type of cold season extratropical cyclone that you may be familiar with is a nor'easter. These are areas of low pressure that generally form over the Gulf of Mexico or the North Atlantic off the coast of Georgia, and then they move north up the East Coast into the New England area, and they are defined by northeasterly winds. And so in meteorology, when we talk about winds, we talk of the direction they are from. And so these cyclones, the winds move around them counterclockwise, and so the airflow would come from the northeast, even though the storm originated in the Gulf of Mexico. And then sou'easters, which is not a typo, even though Google tends to think that when I try to search it, as you might guess from the name, have winds that come from the southeast when they are in New England. So some of these storms are also start as nor'easters. However, they can also form from other areas such as Colorado lows or that tract across the Great Lakes region or other similar paths. Yeah. So these that end up as sou'easters, they generally track inland if they start as nor'easters into Quebec. And so you still have that same counterclockwise flow. However, since Maine and New England are on the other side of it, that gives you southeasterly flow instead of northeasterly. This is the specific storm that I'm talking to you about today. It started off as a nor'easter that, with the low pressure that formed in the Gulf of Mexico, it then moved across Florida into the North Atlantic and then north, where it eventually collided with a high pressure blocking pattern, which then forced it to move inland into Quebec, where it then slowed down and stalled for several days, and led to wind gusts that exceed 70 miles per hour and dropped 4 to 7 inches of rain in western Maine. As you can imagine, 4 to 7 inches of rain in western Maine during the winter, where we're supposed to be getting snow, can be pretty damaging to the area. This lovely picture is of the Kennebec during that time period. And that's not what many of you probably know, that's not what the Kennebec usually looks like. The downtown Augusta flooded. The river rose to 22.5 feet, which is 4 more than the major flooding benchmark, as you can see in the graph there. The Androscoggin River, which I unfortunately do not have imagery from, actually exceeded its previous record flooding, which was in April of 1987. Another impact of this storm comes from the wind gusts, which knocked out power for about a week in some places in Maine. If you were here during that time, you probably remember this storm because power was out for a long time. I remember when I was during this time, I thankfully did not lose power, but I remember coming back and meeting with some other people on the project I was then working with and them talking about still not having power at that time. So these are just a couple of the headlines from the news that came out of that storm. So what am I doing about this storm? One of the things I'm looking at is the power outages, and I will then be pairing it with downscaled wind analysis, which I will get into a little bit later. But these two graphs show power outages. The one on the left is circuit level data that Versant has graciously provided me. And so this was at the height of that. It was at the peak of those outages before they started to fix everything and near the end of the storm. The one on the right, which has numbers that unfortunately might be a little too small to read. However, that is county level data provided by NWS Gray. I have not been able to contact CMP to get data directly from them. However, the highest number of outages were in Cumberland with 71,000, Kennebec with 67,000, and Androscoggin County with 40,000 power outages from that one storm. Next thing I'm doing is I am using ERA5 reanalysis data to look at the storm and better analyze the meteorology. I then compare the ERA5 wind gusts to circuit level outage data, the circuit level outage data that I just showed you from Versant, to try to pair how those winds and the electrical outage locations match up. I then am using the weather research and forecasting model to produce high resolution downscaled meteorology to better analyze this data and to conduct sensitivity tests by increasing or decreasing the sea surface temperature to see how that would have hypothetically impacted the storm. And then I am going to validate my control simulation against surface observations. And so here are just a couple of those results. This is the control from the storm. You can see my outer domain from the WRF model, and then domain 2, which shows the New England area and the temperature and mean sea level pressure. Here is the wind speed from the sensitivity tests and the two difference maps. It's kind of hard to see what is going on in it there. There's a lot of, I suspect the bright areas in the ocean are a product of how of the function that increased the sea surface temperature on my original data. The precipitation is what you would expect from a warming climate, I think, where you have more with higher sea surface temperatures. And so my future work, it involves trying to get the full outage data. So this would be actually getting the data from CMP and Eastern Maine Co-op, doing model validation using global historical climate network surface data. And then I have another storm, and another thing we'd like to do is conduct a pseudo global warming approach to the work output and develop a full climatology of sou'easters. And special thanks to my advisor, my committee, Versant and NWS Gray for providing me with the electrical outage data, and NSF for providing funding.
So you showed a map of outages that showed that all the outages were in the northeast half of Maine and they weren't in the southwest half. Is that entirely a result of the action of the cyclone, or does it have to do with socioeconomic factors?
That is
the quality of the grid system.
That has entirely to do with where the data comes from. So this the
I did quite get to it, but the map on the left is from Versant, and so that is their service area.
That's right, so, okay.
Yeah, and the map on the right is NWS Gray's NWS Gray's forecasting area, and which is where I got the other data from.
Thank you.
Next up, we have Jacob Holmes, and they will be presenting on ground truth and direct observations of subglacial hydrology and sediment controls on basal stability.
Thank you. Hello, everyone. I'd like to talk to you today about upcoming work that we'll be doing this summer at Taku Glacier, the terminus, in association with Wussel and Dougal Hansen's team. They're looking at some of the more complicated dynamics of underlying sediments and deformable beds, right? So I'm interested in ground truthing and characterizing the bed at these locations. So we have a hot water drill and we're using it to access and place geophysical instruments at the terminus of Taku Glacier. If you look up in the center here, you can see this colored velocity map. And you can see that that Piedmont lobe at the end is sort of split into two different sides. One of them has more velocity, one of them has less. So what we're trying to do is create a series of boreholes on each lobe and compare the underlying sediments. At the same time, we'll have co-located 3 different types of ice penetrating radar and a full seismic survey. So normally sliding and movement, the first order control is the pressure, the underlying hydrology. But here, where we have a deformable bed, the main control on that effective pressure, that underlying hydrology, is the deformation of the bed. So a little bit of history on Taku. It was previously, it's the main outlet for the entire Juneau ice field, and it was previously advancing right up until the mid, 20 teens, when almost everything else has gone into retreat. And that's because it is that main outlet. It's got the whole ice field behind it pushing, right? So the main questions we're going to be looking at here is how do subglacial sediments distribution and rheology influence the basal resistance at Taku? How does the basal hydrology modulate the effective pressure and variability on each side of those lobes? And what role does the bed geometry play in local stress transmission and sliding behavior? So the bedding at each of these lobes, we assume that they're different. One may be distributed storage, one may be channelized. And so they'll move in totally different ways. What that does is it creates a fight over driving stress and basal resistance, which I think some of the formatting got messed up going from regular PowerPoint to Google Slides, but I think you can get the general idea. A lot of us have seen this sort of the stress block before. And most of the time we bring this right down to a Coulomb stress equation, but that's not quite enough to wrap everything in when we have such a complicated system under there. There's a big observational gap here because a lot of the data we have and a lot of the observation is inferred. in subglacial environments, they're hard to access. We have very, very, very few direct measurements of these things. And it's in, many modeling papers and systems, you'll find that they acknowledge this uncertainty. So one of the main pushes here is to ground truth and characterize these beds so that we can further constrain our geophysical interpretations of radar and seismic, and we can further constrain our modeling to consider maybe a few more variables once we've collected more data to reduce that observational gap. The methods we'll be using are borehole access. We have this awesome hot water drill that some of you would have heard me talk incessantly about. I've glazed over many eyeballs with. We have a subglacial sediment sampler that we're getting from aquatic research instruments, and we're hoping to collect sediment samples of the actual bed material for characterization. We have some bed sensors. The final determination on exactly what capability they'll have is we're still gathering that. The team has seen what access they have to it, but we're hoping for pressure, temperature, and electrical conductivity. We will also have the ice penetrating radar and seismic that I mentioned, but in addition, we'll have an optical televiewer that has a 360-degree, like 1800 pixel resolution, does full color, and does gamma sensing. So we'll be able to get a really good look at the actual boreholes and the basal environment. So hypotheses that Taku's stability is influenced directly by the deformable sediment accumulation, moreover than the effective pressure, which is the means by which it does that. Bed geometry modulates stress transmission, and direct physical ground truthing and in situ data collection at the bed can improve geophysical interpretation and modeling. Anticipated contributions from this work should be direct bed geometry and sediment characterization for each lobe, as long as we can collect samples at each, depending on how big that sediment is. Multi-site data time series, integrated borehole radar ground truth data sets, and direct constraint of sliding law parameter space there. Are there any questions? Yes.
Do you have any plans to drill anywhere besides the terminus?
Not currently. We have had conversations about in future field seasons moving our way up the terminus to sort of inspect and see how over deepened the bed is there. If we had more time, I would talk a little bit more about how we suspect the Taku Glacier comes down and is marine terminating, but is over deepened far below sea level, just behind that terminus. The terminus is actually grounded on a moraine at the side of the Taku River. So when these sediments redistribute and that moraine erodes, it's possible that there may be marine intrusion and a rapid change in stability there at the terminus. So I'm not totally, it's a higher frequency on an EM spectrum, basically, than what we can see with visible light. And the sensor is primarily an optical red, green, blue. But it also does gamma so that it can still characterize the area in very turbid environments, because this device is also used in like oil drilling or exploration where it may not be clear glacial water that we're looking at. Well, thank you all very much.
All right. So next up, we will have Leo Villicis, and they will be presenting on recent warming following a century of intense local perturbation drives abrupt shifts in northern Maine lakes.
Hello. Hello, dear CCI family. Much like Jacob, I'm very much interested in ground truthing hydrological systems, but much smaller lakes. And yeah, I'm happy to present on what I've been doing and take you back to some of the regional history from all the way to the present. Here we see a beautiful view of Katahdin there in the back on a calm, warm summer day on the shore of Upper Joe Mary Lake, which drains towards Lower Joe Mary Lake, as shown in this map. As much of the lakes in the Joe Mary watershed do. I am focusing today on the Yoke Ponds camp and the sectors in there, which also drain towards Joe Mary Lake and have been the center for logging operations in this sector. Between 1835 and 1935, log driving was used. That means floating the logs towards this watershed. And at the height of these operations, it is said that about 10,000 cords of wood could be driven annually, as depicted here in the historical account by Bill Geller. To make this point a little bit clearer, I've here shown some of the central lakes of the system, and the path for log driving through this. At the head of the system, we have Big Pleasant, which drains towards Yoke Ponds. And then to Crawford, which is the protagonist of the story. That eventually goes to Joe Mary, as I had mentioned already, which is connected to Millinocket, where the Great Northern Paper Company paper mill was located, which at 1908 looked something like that, with, it says 21 million logs. So very intensely used for that industry at that time. To run these large operations, there was camps which housed the workers and the tools and the equipment, much like this example of the Yoke Pond camps, which I've already mentioned in 1892. This is a historical testament of that, but it doesn't show some of the possible perturbations that went on, in this kind of industry, like usually housing about 80 men, 36 horses, building multiple dams, their catastrophic collapse of those dams and demise, and to load tons of wood on it, they would artificially thicken the winter ice. So you can imagine these affect the lake systems. Yoke Pond Camps is alive and well today. Refocused as for fishing enthusiasts and seasonal getaway. I'm again right before lunch, so I've introduced a few elements to capture your attention. Yeah, and of course it houses the certified best whoopie pies in the Millinocket area, thanks to Amanda that runs the camp. Here a mayfly, and as good fishing enthusiasts, the members from the camp have kept detailed observations of their fishing, and they say it's not as good as it used to be. They've also noticed that the mayfly populations, this charismatic insect, is in decline, and that means less food for their fish, and that begs the question, why is this the case? Is it some kind of perturbation-related phenomenon with the whole ecology, or is maybe climate also driving this situation? What I'm showing now is the main anomaly for temperature that you can see go up and up and up since 1940. And we can imagine that this is increasing stratification, which, like the thick cream filling between two whoopie pie halves, separates the top warm layers from the cold, heavy bottom layers of the lake. And we can expect that this would increase anoxia of the bottom waters, which would be detrimental for the larvae of the mayflies, which live much of their lives underwater. Less fish for food. And indeed, the global meta-analyses have shown strong evidence for increase of stratification in recent times, and future projections also, we expect more stratification to occur. And this is where I came along with the hope of providing a historical perspective to the fishing problem. And ta-da, of course, this is done with sediment cores, like the one in the image that I collected with Matilda over there, and my wife. Not Matilda is my wife, but my wife and Matilda, which helped to understand the evolution of this Echo's lake systems. And as I promised last year, with this teaser, you might or might not remember, I promised to go back in time. If you've seen Dark, you might notice that. To reconstruct the lake history, connecting the point with the ecology today. And of course, my passion is diatoms. If you're not familiar with them, they're single-celled microalgae, and they're very abundant, very diverse, and make for great fossils because they have this silica shell of their cell wall, and they, resist decomposition in the sediment. So the objectives are to understand the baseline evolution of Crawford Pond during the last millennium, to get a baseline. But this, I must consider the known history that I mentioned about the logging industry and gauge the impact of that. And then gauge the possible impact of recent warming as seen in meteorological records to get at the main question here, which is, has indeed stratification become longer or stronger in the recent decades, leading to the observed, fishing problem? All right, so to formally introduce my setting, it's here in Maine, but a little more north. And I'm studying two lakes here called Big Pleasant and Crawford, but today I'm just talking about Crawford. So it is very key to understand the ecology today, like to ground truth, like Jacob, but here in Maine. And for that, I went to lake many times between 2024 and 2025, set up temperature strings, got water samples every 3 meters down the lake, and other variables like light, which are important for the ecology. And then for reconstructing the lake, I mentioned we got a lake core and used regular techniques like lead dating, lead to tin dating, and radiocarbon dating, and of course saw the diatom assemblages down in the core. That's actually a picture of a live a cell I captured from the water column. So this is the result of that stratigraphy of the age depth model for the Crawford Pond with 2 radiocarbon dates and a series of lead to tin datings. It was 83 centimeters long and around 80 centimeters. It gives us an age about 1,000 years back in time. There's an accelerated sedimentation rate that gives us about, at 20 centimeters depth, 1950 Common Era. And the most abundant diatoms in the modern and sediment setting are the heavy Alagacira, the snowflake-like Asterinella, the very delicate Urosolinia, and the robust chain-forming Tabularia. To synthesize the data I'm showing here, this is from the water samples, and I've cut the slices up into the dominant species. So first Alagacira in spring, as you can see in this graph. Then as summer brings hotter waters, there's an increase in Asterinella and Urosolinia, coinciding with the hottest temperatures. And then Tabularia takes the dominance during fall. And now drum roll for the core results. So the core results are these for the last 1,000 years from left to right. At the top, I'm showing the same temperature record I showed at the beginning. At the bottom, lower, the spring and summer dominant species, Asterinella and Alagacira. And we can see that they have relatively low values compared to the high values of the fall dominant species, Tabularia. The gray banner marks the logging era, and we can see all species kind of went down and increased at the height of the logging era. But then afterwards, we see a sharp increase in the summer and spring species and a decline to a record minimum in the low species, in the fall species. Zooming in, we can take away that the logging era, the biggest changes weren't during the logging era, but tend to coincide with some warming that happens after 1996, where we see this occurrence of the Ursulina kind of appear and increase. So to wrap this up, the main takeaway is, well, the largest change in the last millennium was not during the logging industry, but afterwards. And it seems that the physical impact of logging in comparison was small in comparison to the community restructuring of the temperature increase. This is supported by the appearance of this species, and this could signify that Ursulina could be a possible stratification proxy, and this would, support the hypothesis of recent stratification. But, like whoopie pies, but is this unprecedented warming or a compound perturbation? I will climb up now and just show some of the data I will expand to, and really appreciate your attention and all the help from all the helpers, especially, and the other funding organisms. Thank you. That's them. Questions, I guess. Cool, thank you.
All right, and for our final presentation before we break for lunch, Wyatt will be presenting their research on combining UAV remote sensing with in situ snow pits and co-located automated weather data to make high spatiotemporal resolution. Take it away.
Thank you. Thanks, Leo, for making me hungry right before lunch. So today I'll be presenting some of my thesis work, and more specifically the broader significance, and then I'll kind of get into where I'm at the very end. So to start, let's talk about why we care about estimating snowpack water storage. So for starters, a quarter to a third of the global population relies on snow water resources for agriculture and drinking water. And on the figure on the right, you can see the Western United States, and the shaded area is areas that receive snow. And this represents how the snow gets transferred from high mountain regions down to cities. The blue dots represent reservoir, and the blue lines are rivers, and the red lines are conveyance infrastructure that they've built to, again, transport this water. So when we talk about snowpack water storage, we're talking about snow water equivalent, or SWE. And SWE is essentially the depth of water you would get if you were to melt down a specific area of snow. And SWE is a function of the depth and the density. And it's important to make the distinction initially that we're talking about wet snow here, which is the type of snow that you can kind of form a snowball with or make a snowman. And the figure below on the x-axis is time, and this is showing 2 years. The gray is SWE, and the blue is snow melt rate. And as you can see, in the high SWE year, we have much higher flow, much higher melt, and the timing of this is also important, right? Because this happens very quickly. And on the contrary, the lower peak SWE year, you have lower melt rates, and it's also spread out more over time in relation to its amplitude. So let's kind of break this down and talk about the impacts. So for high peak SWE, we get, again, faster melt rate, higher flow, and more water overall. This can cause flooding, as we saw earlier. Again, extreme flow events can cause negative impacts to ecosystems, but it also provides more water. On the contrary, lower peak SWE year, we have lower melt rates, lower flow, less water. Less water overall throughout the season increases susceptibility to wildfires, specifically in the Western United States. It also can cause warmer water, which again negatively impacts species. And excuse me. Yeah, this kind of summarizes why we want to predict snow water equivalent and why we want to estimate it. So we have two problems with this. Oh, okay. Anyway, we have two problems with this. First is SWE varies a lot spatially, right? And again, SWE is a function of the depth and the density. So SWE varies in relation to topography, vegetation, metamorphism of the snow, wind compaction and redistribution, formation of ice layers, as well as a unknown liquid water content. And this figure is from Keegan Bellamy, who is a student here, and she did some multi-offset radar profiles in Maine, and the lighter areas along the profile show higher SWE, and the darker or the black areas show low SWE or no SWE. And on the top, you can see it's changed kind of in relation to topography and aspect. And then on the bottom, you can see it's changed in relation to biomass. The point is that SWE varies across space. Okay, so what's supposed to happen? Cool. Our second problem is that our current methods have high uncertainty. So we look at a few different scales when we're looking at this. First, global scale, and the methods that we use for that have really high resolution, typically 25 square kilometers or more. On a regional scale, we typically use point measurements, such as here in Maine and then in the Western United States. And these measurements are extrapolated over very large areas. And you can see this diagram is from 2026 from the Maine Cooperative Snow Survey Program. And you can see SWE is varying greatly through the winter season. You can also see a difference in where they're sampling. This is kind of important because the previous figure I showed where Keegan did her work, part of her work, she was working within kind of an area that had one point measurement that was supposed to represent 19,000 square kilometers. And then on the smaller watershed scale, we typically use ground penetrating radar. And as we've heard from other people, and I'll say again, the water content greatly affects our signal. And because it affects our signal, it impacts our SWE estimates. So this gets into kind of where I'm at in my work. So I'm collecting repeat LiDAR data sets I have here in Maine on campus, actually. And I'm collecting snow pits for snow water equivalent data. And then we also have a co-located automated weather station as well. And my goal is to map the snow depth very accurately because here in Maine, where we get shallow snowpacks, the depth tends to vary much more than density. So it's very useful to have accurate snow depth data. And I plan on doing this by eventually differencing rasters to map it. And the point here is that these small scale estimates are important because we use them to ground truth our larger scale estimates. But we've run into a few challenges, mainly with this guy, our inertial navigation system. Our inertial navigation system is a series of gyroscopes and accelerometers, and it's responsible for measuring the angle at which the LiDAR system is at in the air. It also helps fill in the gaps between our GPS points that we're collecting on the equipment. So let's kind of look at some of the data that I've collected and some of the issues. So on the left here, you can see that, sorry, let me back up. Let's talk about why the INS has issues first. The INS, we've been having issues with the INS because there's been some issues from the manufacturer, some settings that weren't quite right, and a few other things. It's not super important, but we're working with the manufacturer to resolve them. But you can see we have two examples of a drone shooting lasers down at the ground, and you can see what our true orientation is versus when our INS has errors, it has a different perceived orientation, which can offset our data. And you can see this on the right where I have two flight lines. They're overlapping. The colored areas are where these point clouds do intersect and overlap. And the red represents areas where these point clouds don't really agree with each other. And the green represents areas where they do. So we can kind of look at this in 3D. This is a different part of that same survey. And as you can see, we have one point cloud here from one flight line. And then as we come back around, we have another flight line and it's kind of offset vertically. So we can look at that in 2D. And then we will look at in a cross-track profile next through this data. And what that looks like is this. We have the orange points representing one
flight line, and the blue points representing another. And as you can see down on the right, is we have about a meter between these layers after all the post-processing. And even on the blue flight line, we have 0.6 meters between the points in the same layer, and this is because of these same issues. In addition to this, we also have horizontal displacements, which could, be part of this, but yeah, everything's working in 3D. So that's all I have for you guys today. Thank you for everybody that funds me and helps me in the field, and of course all my lab group. So yeah, thanks.
So you probably said this, but is the purpose of this study ultimately to be able to predict the presence of SWE and then mitigate the possible consequences, good and bad?
Yeah, exactly. Yeah, being able to predict flooding and rain on snow events and how much water is actually stored in the snowpack is the goal. Yeah. More questions, guys? Awesome.
Well, Wyatt, can I ask a question?
Yeah, sure. Go ahead, Ryan.
So I missed that last part. So is the issue in the overlapping area only, or is it extend beyond into the areas that do not overlap? In other words, is a simple offset a uniform offset in that overlapping section, or is there a linear ramp that occurs in there?
It's a little more complicated than that because it's existing in 3D. We're getting both navigational errors from our INS because when you post-process this data alongside the GNSS data, it actually affects the actual position of the sensor. It also is responsible for angular measurements, which then propagate over a distance, which can result in large errors. Hopefully that answers your question. I guess the answer is no. Basically, all of the points within the point cloud are essentially wrong to a degree, have very high uncertainty.
Maybe we can meet. I'll be in town next week. Maybe we can meet sometime.
Totally, yeah.
Talk about it.
Yeah, absolutely. Yeah.
Thank you.
Esther?
Yeah, this is really cool. I was just wondering what is the next step? How do you go from an elevation profile to, or is it just getting that depth being a major component of SWE and just getting that depth, and then there's other steps to get to SWE?
Yeah, exactly. That's why we collected snow pit data around our study site. So yeah, does that answer your question? Yes. Yeah. Cool. Thanks, everybody. Welcome back after lunch. I hope that you enjoyed the refreshments if you're here in person. We're going to start off session 7 with the Jacobson CCI Distinguished Service Award presented by the 2026 Jacobson Committee. So I invite the members of those up. Can one of you be on camera?
Oh.
Thank you.
I'll be the beautiful face.
Thanks, Alex.
You want to start off? Yes. Okay, so the Jacobson Award has some basic criteria. It recognizes faculty and staff of the Climate Change Institute who have, over the course of their careers, performed outstanding service above and beyond their professional duties, often having a local, regional, or even global impact. Nominees are recommended and evaluated by a committee of 3 CCI students with historical perspectives from the previous year's recipient of the award. This year by Dr. Bonnie Newsom. The nominees are evaluated by the magnitude of their impact, the value of their service to the CCI and beyond, to the extent to which the service has gone above and beyond their career professional accomplishments, and the length of their service to CCI.
Well, this year, the award committee recognizes Dr. Jasmine Saros. We recognize her for her exceptional record of service and leadership. Jasmine is a professor of paleontology in the Climate Change Institute and School of Biology and Ecology and Associate Director of CCI. In these roles, Jasmine has raised the bar for research, not only develops new knowledge, but positively impacts students and communities from the university to the international stage. Her career in lake ecology over the 25 plus years have been replete with grant procurement successes, including, of course, the NSF-funded IGERT and the NRT programs that have supported over 40 students and shaped the next generation of lake, climate, and Arctic scientists. Alongside her 15 years as CCI Associate Director, a major contribution in itself, Jasmine has served as Director for the UMaine EES program and the Sawyer Water Research Laboratory, using these roles to foster collaborations across vast scales. Locally, she has been deeply involved in tracking the recent and historical evolution of Maine lakes, which affect the livelihood of thousands of local residents. Nationally, she has implemented state-of-the-art lake science to remote alpine and boreal lake regions, establishing the effects of abrupt climate change and nitrogen deposition. Internationally, she has led expeditions to Greenland since 2011, investigating the ecological and social implications of rapidly warming Arctic. These examples not only begin to reflect the breadth of her contribution, but clearly demonstrate service that has gone above and beyond, leaving no doubt that Jasmine is an outstanding member of the CCI community.
Yeah, I'll say things. I guess I'm supposed to be. Thank you so much. I'm totally shocked. I really appreciate this. It's such an honor to be part of this institute. It really is. And I've really enjoyed working with everyone here in all of those different capacities. I'm stepping down as associate director. I'm really looking forward to seeing who steps up next to be associate director. I think they'll bring some nice new perspectives to the position. CCI is the reason I came to UMaine, and it's the reason why I'm here at UMaine. So I hope that all of you recognize just how valuable it is to have such a great group of students, staff, and faculty who work together like this. So thank you so much.
Congratulations to Dr. Saros. As we enter into our current session, our session is now faculty talks. And our first presenter will be, sorry, it's a different format, so I'm just gonna get this over here. Yeah, I'm gonna figure out how to share this one in particular, because that's not on the screen share. So apologies for momentary technical difficulties. Soon, I'm just going to reshare this particular screen. There we go. And oh, but I also need to get it up there. Would you mind? Could I get some assistance? Thank you, Avery. Avery and I are the tech support team here. I'm not sure how to get PDF. Please hold on Zoom. Thank you very much.
Now, can we move to it, okay? Yeah.
Look into it.
Look into it.
Okay.
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 You can't see it on the computer screen, but you can see it.
Okay, that's all right.
Thank you for bearing with us on that one. Thank you, Avery. Our first speaker in the faculty session is Dr. Bonnie Newsom presenting Potter's Choice and Wabanaki Sociospatial Organization, an archaeological exploration of the Kennebec River boundary hypothesis.
Thank you very much. Hello, everyone. It's good to be here. Thank you to the technology support. I really appreciate that always. So I want to start by acknowledging that the ceramics I'm discussing today come from the ancestral homelands of the Wabanaki peoples, the Penobscot, Passamaquoddy, Maliseet, Mi'kmaq, and Abenaki, whose descendants are still here, still connected to these landscapes, but also still connected to the material culture that I'll be talking about today. And that context matters for everything that I'm about to share with you, because this research really feeds the reawakening of pottery among Wabanaki peoples. And this project uses ceramic data from over 600 ceramic vessel lots to test a long-standing archaeological hypothesis that the Kennebec River in Maine marks a significant sociocultural boundary, dividing distinct pre-contact indigenous groups. And I'll walk through that data today and show you how that works and how it doesn't. So why has the Kennebec been proposed as a boundary at all? Well, several lines of prior evidence have been cited. Projectile point studies by Dr. Brian Robinson at the Lavana site on the Sebasticook, which is a Kennebec tributary, showed two co-occurring projectile point types made from very different raw materials. Side notch points, as you see kind of in the center of the top center of the image, were made from northern kind of exotic materials, cherts, and generally these are from interior Maine and Nova Scotia, suggesting social connections to Penobscot country and Maritimes. Lavana triangles, which is the projectile point on the left, were made from local stone, suggesting a different interaction sphere. And there's also a horticultural frontier argument that maize and beans appear in westerly or southwesterly assemblages, but are absent east of the Kennebec until the protohistoric period. So the boundary hypothesis has a real foundation, but it's never been rigorously tested with ceramics, and that's what I'm attempting to do here. This is a single fragmentary vessel, but it's not just an object. Every choice embedded in this pot, what clay was selected, how it was tempered, the way the rim was finished, how the surface was treated, reflects a learned practice, and it's a choice people are making. And those practices are social. They're transmitted through communities, repeated across generations, and when we look at those choices across hundreds of vessels, ceramics become one of our strongest data sets for tracking similarity and difference among peoples in the past. Oh, let me just go back. This is actually from the Eddington Bend site, which is right up the road. Often. So what might ceramics show? Well, if the Kennebec represents a genuine sociocultural boundary, we would expect distinct temper compositions. Temper is the additive materials that you include in clay to improve pot performance and strength. Temper compositions reflecting separate raw material procurement zones, consistent differences in vessel morphology, non-overlapping decorative traditions, and stable isotope values can show culturally patterned dietary differences, not just a coastal to interior ecological gradient, but can be signatures for things like corn. And these aren't subjective judgments, they're measurable expectations, and they're either supported by the data or they're not. This is a data set. It consists of 640 ceramic vessel lots. Now, that's not always the whole vessel. We may only have 1 or 2 sherds available to assign to a particular vessel. And they're from 5 locations across Maine and associated with different water bodies. I recorded over 20 attributes per vessel, and these include temper type, and density, rim eversion, rim and body thickness, orifice or opening diameter, surface treatment, and decorative techniques such as cordage twist direction. I also ran 14 AMS dates, and these were obtained on charred food residues that are still adhering to the interior or sometimes the exterior if something bubbled over of the vessel. And we're able to get carbon isotope values from those samples and as well as radiocarbon dates, giving us both chronological control, but also subsistence data from the same vessels. Here are the 5 locations: the Penobscot, Kennebec rivers, Penobscot Bay, Damerscott River, and Frenchman Bay. The samples are from legacy collections held at institutions across Maine, and many of them have been curated in these institutions over the past century. Both are coastal and interior samples, and the Kennebec runs, you can see here, runs roughly through the center of the study area, and that is the proposed boundary between what people are saying are 2 different groups of people. Here's a temporal breakdown. Before comparing assemblages, we need to account for time because ceramics change through time, and we don't want to compare ceramics that are later to ceramics that are earlier. And these collections are not all contemporaneous. Penobscot sample is heavily weighted towards ceramic period 2, and largely because the Eddington Bend site is a very large assemblage. Penobscot Bay shows use spanning CP2 through 5. And for cross-site comparisons, I focused specifically on ceramic period 2. I wanted to have some temporal constraints on the sample before making any interpretations. And so I think using CP2 is important in part because that's the time period where we see people making the most pots. Pottery seems to fluoresce at this time. This slide compares the frequencies of major decorative techniques in ceramic period 2 vessels across different drainages. The key point here is that the same suite of decorative techniques appears across regions, but they're used in markedly different proportions. In the Penobscot River and Penobscot Bay assemblages, punctate, which is the little holes you see there, that decoration is common, particularly in Penobscot Bay, and dentate stamping is also frequent. In contrast, punctate decoration is very rare in the Kennebec River assemblage. Instead, Kennebec vessels show higher proportions of what's called rocker dentate and pseudo scallop shell decoration, techniques that are not unique to the Kennebec, but are clearly emphasized here. Damerscott stands out as most having overwhelmingly high frequencies of dentate rock decoration, suggesting strong local patterning at that drainage. I had a student do the Damerscott sample, so this could be reflective of different analysts, which is also a question worthy of exploration. What's important is that these differences represent variation in emphasis, not the presence or absence of a decorative tradition. And this pattern is consistent with shared technological knowledge across the region expressed through localized choices rather than a sharp cultural boundary of the Kennebec River. So here are some examples of what the just a table and some examples of what the decorative techniques look like. You see the punctate in the one on your left. That's dentate rocked. Oh my goodness. And in the center is dentate stamped. And on the far right is what's called pseudo scallop. And all of these are techniques use a toothed implement. However, they're using things differently. I'm a slow talker, so I'm not going to be able to get through all this, but that's okay. Temper, which is the additive material, the aplastic material that people include in pots, shows some patterning as well. Penobscot River assemblage is heavy in quartz, where the Kennebec is heavy in feldspar. And this is, we don't know whether or not this is a reflection of the local geology or whether it's human choice. Each of these materials has a particular feature that makes it useful for particular characteristics of the pot. So it could be people are choosing for these. Rim inversion, we also see patterns here, the outward flare of the vessel lip. So not all pots are constructed the same way. Some flare out on the rim, some flare in. And we see distinctions here as well. And I'm not going to spend a lot of time on that because I'm running out of time, but thank you. We also see differences in vessel orifice diameter. So the average orifice diameter amongst each of these locations differs. And you'll notice that the Kennebec orifice is much higher than the others. So we suspect they may have been cooking for more people, but that's something to be tested for. Here are my radiocarbon dates. And you'll see that these are all on food residues. So it tells you exactly when the pot was used. So I've got the clam up sign, sorry. I'm a slow speaker, and but I welcome any questions that you might have. Yeah, Dan.
So one question I had, you showed a map of where the sites were, and the westernmost ones were right on the Kennebec.
Yes.
If you really want to test whether there's a difference on the other side of the Kennebec, don't you need sites from there?
Yes,
Do they
absolutely.
exist, or have they not been excavated?
No, they exist. I just haven't gotten that far yet. Yeah,
So
but
we could, next year you'll update with.
yeah, if I can get to access to some of those collections west of the Kennebec, certainly. But I think
Neat study.
I think we do see though that corn is being grown on the Kennebec. So the stable isotope data on these particular samples
That's supposed to be the border, right?
didn't show any evidence of corn. So yeah, but corn is visible in places like Norwich Walk. Yeah, thank you all.
Can I ask a quick question?
Sure.
So what's your preliminary judgment? You didn't quite get.
I know, I didn't get to the answer. Well, right now, I don't think that it's a hard set boundary. I think that it is actually, you have this large tradition that has similarities in decorative techniques and technology and all of those things. But then you have these little localized areas where people are making choices for whatever reason that distinguishes between the two. And so the Kennebec, there's got to be some interaction in these regions in order for that overall, those overall similarities to occur. Yeah. Thank you very much.
Just one moment. Our next speaker is Dr. Rupert Nason, speaking on effects of biochar quality and tree species on soil carbon and water retention.
Thank you very much for the opportunity to join your session today. I got to keep it quick since I'm only given nominally 2 minutes. A couple of brief overviews. This is a container garden study up at the University of Maine at Fort Kent. Much of the labor is contributed by undergraduate students, and yes, I am still looking for potentially one more to join the team this summer. The main research question is, can biochar soil amendment increase soil carbon storage for long term as well as water retention in tree plantings? Brief overview of the experimental design. We've got 256 potted trees representing 4 species, 2 broadleaves, 2 conifers, treated with either no biochar or 10% volume of one of 3 different types of biochar. Those include charcoals from traditional combustion process or a chemically derived material from biofuel production. The couple of graphs for data. The initial findings, which go back a year, show that within a few weeks of the time that the biochar amendment was applied, we do see increased soil respiration rates, again, in the realm of 10 to 50 micromoles per square meter per second. In the 1.5 years later time point, so that is last fall, those respiration rates dropped by quite a bit. The soil organic carbon has stabilized, and there's still visible black carbon biochar in that soil. Also noted that the average soil moisture is about 25% higher in the situations where there is biochar amendment. So take-home messages are that biochar does seem to increase at least intermediate-term soil carbon storage, good for climate, and also increase soil moisture, which is good for trees, particularly in drought-stressed areas. Thank you to all of my sponsors. I'll take any questions. Yeah, go for it.
For the tree species that you chose, are all of them native to the Fort Kent area, or are some of them out of their element?
3 of them are, so it was balsam poplar, sugar maple, white spruce, and then the one non-native is Norway spruce that J.D. Irving is very interested in using as a commercial forest product species.
Other questions?
Yeah. Oh yeah, go ahead. You were first.
What is the significance of increased soil respiration? I'm trying to figure out how that factors into good or bad.
Basically, I want to see if the carbon that we add to the soil is actually staying in the soil. Some of it is, some of it isn't, but again, the study is not complete yet, but the long-term trajectory does seem to be that more of that carbon that we add in the form of biochar is staying in the soil.
But is the increase in respiration then just a sign that more carbon was added that's respiring?
Right. So you add more carbon, you're going to lose more.
Right.
And the kind of final result is going to be to confirm what these data are suggesting, that you do in fact store more carbon when you put that very recalcitrant material into soil.
Thank you.
Yeah. I don't know if we have time for your question.
We have time.
Yeah.
Okay.
Real quick.
I apologize if this is way too far outside the scope of your work, but I've heard some things about biochar perhaps showing promise in terms of binding PFAS. Is this of any interest to you? Do you know anything?
Yes and yes. My short answer is I've actually been talking with Professor Ling Li about this. We're going to be looking at getting some grant funding. Biochar, like any type of charcoal, has a lot of surface area, high absorptive capacity. So that's my quick answer. I'm happy to chat more later on when we have time.
Thanks.
Thank you very much. Our next speaker is Dr. Jasmine Saros, speaking on biogeochemical cycles of subarctic agroecosystems, quantifying system properties, and forecasting future scenarios.
So I just wanted to give a quick update. This is a new project that is a collaborative interdisciplinary project involving 7 members of CCI and 2 additional researchers at UMaine, as well as our Greenlandic research collaborator as well. It's focused on South Greenland, and it's a project that was co-developed with sheep farmers in South Greenland and reflects their concerns about how changing drought frequency and severity is influencing food security in this area. And so our project is focused on the objectives listed there, but sort of in a nutshell, thinking about the current freshwater demand in the area and some of the challenges associated with changing climate conditions, looking at feedbacks among water, nitrogen, and phosphorus cycles, because we want to think not only about the water quantity, but also the quality as we're getting changes in water supply there. And then developing future climate scenarios for this area and assessing impacts on land surface hydrology. So as I mentioned, this is a project that was co-developed with farmers. And so the relationships that we've built there are really important. And it's been a good process to go through, a lengthy process and a really rewarding one. But I'll just mention that it all started in 2019. Paul Mayevsky and Charles Norkey received a grant from the UMaine Research Reinvestment Fund that took 19 faculty across the UMaine system to this area. We had a chance to meet with all sorts of people, but as part of that, I met with some sheep farmers and learned about the concerns with drought. That actually helped us secure the NSF SANA NRT, not just the drought work, but other work as well. But that was an important piece of that. And as part of that, Amanda Gavin has been working on reconstructing drought in the area over the last few centuries. That's helped to lay some of the groundwork for the current project as well. And we also received a UMaine Arctic Seed Grant. So largely through Kristen Schild's efforts leading UMaine Arctic, there was a seed grant program. So for $25,000, we were able to add some additional work to this area. I'm almost there. So we've been there multiple times working with the farmers while we've been there. We've also maintained communication with them by providing newsletters that are translated into Greenlandic so that while we're not there, we can continue that relationship. But I wanted to point out that, it's very important to get this seed funding. I know UMaine doesn't have much right now, but I just wanted to make sure we keep that on our radar about how important that is. Having that little bit of seed funding, our return on investment just from the 2 projects I'm part of is over 45. So we brought in $45 for every $1 UMaine gave us. So I hope we can continue to do more of that as an institute. So, right.
Questions for Dr. Sells?
Yeah.
What was the process of initiating contact and then building those relationships?
Yeah, so in this area, it was facilitated by the fact that the Sheep Farmers are organization, and the president of the Sheep Farmer Association hosts people to come visit her farm, and she hosts like a coffee where you can sit down with her and talk about concerns. They had a number of different concerns, but the climate one is one that I was able to chat more about with her. And then she's connected, of course, to the whole sheep farming community, and that really opened the door for us to talk with additional farmers as well. So.
Thank you very much.
Thank you.
Just gonna be me.
Yeah, yes. Our next presenter is Dr. Scott Braddock, presenting on the Juneau Ice Field as a polar proving ground for collaborative science, technology development, and workforce training.
Thank you. So I'm here speaking on behalf of our full team, which has grown significantly in the last few years. So that's why you see a few names on there. Myself, Ryan Casoto, Peter Strand, and most of these funding efforts are led by Seth Campbell. So I want to talk about this polar proving ground concept that we've been developing over the last, many years, but at least in the last 4 or 5 years, it's really kickstarted some of the federal appropriation funding that we've been able to receive as a group. You've heard a bunch of amazing talks about the research going on the ice field from Kaylee, Renee, Jake, Wyatt, Matilda, many others. So you heard a lot of that over the last few days. That's just a sample of some of the research we have going on under this larger polar proving ground concept. And essentially what that means is it's extremely expensive and even harder and harder to get to places like Antarctica or Greenland these days. So we are using the Juneau ice field in two ways, both to bring researchers there to study the ice field itself and how we can use that as an analog for what's happening in the wider Arctic with glaciers, but also as a cost-saving field site to test your equipment. So if you have a new concept or piece of geophysical equipment, you're not sure if it's going to work in Antarctica, you've just developed it in your lab, you can come to Juneau ice field for a fraction of the price, test it, go to NSF for additional funding and prove that it actually works in the field. And we've had great success with bringing teams up to the ice field for that. And I mentioned with this funding, we've grown our team as well. So myself, Peter Strand, Ryan Casoto, who's on Zoom, we're all research faculty that are now part of CCI. That were brought in on the funding under this that Seth has led. We have a ton of new graduate students, well, current ones and new ones coming in as well that are going to be part of this initiative. So the research is ongoing. You'll continue, the different research kind of pathways are ongoing. So you'll keep hearing about those over the years. But what I wanted to stress and talk about today is this new JERP graduate program. So you've probably heard Seth talk many times about the undergraduate program that I was part of myself. But Seth and others kind of envision there are other ways that JERP can kind of include people in the cryosphere community. So that's both with high school students, which we've had a lot of success with over the last 3 or 4 years. And now we're starting this graduate program that's focused on bringing in graduate students from around this year, just the US. We're going to open it up internationally once things become a little more clear as far as bringing in students from around the world. But this is our committee in year one. This includes research faculty. We have the team from UMaine here, Seth, Ryan, myself, and Pete, as well as Dan Dixon, who many of you know, Lynn Kaluzinski, who just finished up a position at University of Alaska Southeast. She was a PhD student? Yeah. Kaya Riverman as well, and then Jill McCookie, who's out of Tennessee. And this is going to be a month-long program bringing in these graduate students from around the US. We have many UMaine students participating. So as I talk about this, if you're a UMaine student working in this cryosphere umbrella, and this is something that interests you, come talk to us. We're bringing 13 students up for about a month. They're going to essentially use this program to learn how to become a polar scientist, how to work on an expedition. So they'll get safety skills. And then they'll be incorporated directly into funded research. And that funded research includes from the Cold Regions Research and Engineering Laboratory. I think we have NASA coming up there this year, NSF funding. So those students will get direct hands-on experience working with faculty on their projects. And another component of that is that each of those students will take that experience and then back home, they'll share it with a high school program in their communities. So they'll develop a lesson out of the research they do on the ice field that they can then share. And we're just trying to broaden the scope of who we reach under this larger funding and polar proving ground concept. And we feel that this JERP graduate program is going to be an amazing next step towards that. And if there's anything I missed, Seth, repeat. That all sounds good. Give us on here so we can get 6 minutes, but I don't know if I need it. 2 minutes left. I'll just open it up to questions. That's most of what I want to say today. And I hope that if this is of interest to you as a research faculty or a graduate student to be involved in this program, you've kind of seen the range of research a lot of the students are already doing on the Juneau ice field. Come talk to Seth or I or Pete here in person. We're already working with the forestry department, the engineering department, others within CCI, and then many other collaborators outside of UMaine. So yeah, quite the team going. Thank you.
Questions for Dr. Brad? Thank you very much.
We have about 10 minutes, a short break until the scheduled beginning of Dr. Burkle's
alumnus lecture.
Alumnus lecture. Thank you very much. Sorry, I lost my paper. So see you at 1:30. As a matter of fact, actually, As a matter of fact, actually, I've just been informed that Dr. Burkle is ready to begin now. So if we want to move into that as well, if we can just kind of get rolling.
Super. Thank you, Thomas. Appreciate it. All right, it's my pleasure to introduce this year's alumnus lecturer, Dr. Sean Burkle. Sean did his PhD here. Oh, he is now an assistant professor. No, you're about to be promoted. You've been promoted, right?
As of July 1st.
As of July 1st, he will be a tenured associate professor, both in the Climate Change Institute and in cooperative extension. And he is also the Maine State climatologist. Sean.
Thank you very much. Okay. Well, good afternoon, everyone. And bear with me just for a moment. I want to change modes on the display if I can. Yes. Maybe all I need to do is resize it. I'll be fine. I'm all set. Okay. What you're not supposed to do when you show slides is to read all the text, but there are some of the slides here in which I think that would be helpful. I want to make sure I can read it on the screen. And so as you have heard from Dan's introduction, and as you can see on the slide here, I would like to give a presentation on Maine's coldest winters and some really, what I think are really interesting historical events in which Penobscot Bay, as well as other bays and harbors along the Maine coast, and even all the way down to Chesapeake Bay, would freeze over during some of the coldest winters. I think these events provide important historical climate context for climate change that is happening now. And it's the kind of thing that many people who are from Maine or the region more broadly, they have relatives, parents or grandparents who experienced at least the latest of these events. So there's still some living memory. It's also recorded in photographs, in newspaper articles, and various books. So I want to go through that with you today. But where this is an alumnus talk, I also want to give you an overview of my time at CCI as a graduate student. We'll do that in a moment. Just to carry on this thought about context from historical documents and as well as anecdotal information. Whenever I give a public talk as a state climatologist, depending on the setting, if it's say a garden club or an outdoor recreation group, yeah, I'll give the talk about the climate impacts in Maine, but I also like to hear anecdotal stories, what people remember from when they were younger, or even 10 years ago, things that stand out in their minds as things are a little different now than they used to be. This is just a sampling of some of the documents that you'll see later. This history of Castine, Penobscot, in Brooksville, published in 1875, an Islesboro sketch published in 1890. A journal publication from 1954 documenting and detailing Hurricanes Carol and Edna, two hurricanes that impacted New England and Maine 10 days apart from one another in 1954. Pretty unusual. And then various photographs. Over the photograph in the corners from 1907, schooner and sea ice off of Lubec. And as I mentioned, before we get to that part of the talk, I would like to present my academic journey. It's a bit non-standard because I've been at UMaine a long time. I got all my degrees here, and I realize it's much more typical for faculty to have backgrounds at different institutions. And for me, it just happened to be that I stayed in the same place more or less, but I did get to go into the field on a number of occasions, which you'll see. And then after that, we'll delve into Maine's climate history and Penobscot Bay. My academic journey. I started at UMaine as an undergraduate student, technically in the fall of 1996 as a physics major. After about a week and a half, I withdrew because I realized I was in over my head in terms of math. I'm an average math student, and physics I could tell it would have been quite a struggle. So I took the year off and I came back as a geological science student. So this was when the School of Earth and Climate Sciences was the Department of Geology. And um, and so between 1997 and 2002, I got my Bachelor's of Science there. Now, my interest in climate came about from meeting people in the Institute as well as in Earth Sciences. But in particular, my sophomore year, George Denton was assigned my advisor for the year. And it was in meeting with George, and George was finding about the classes I was taking, what my interests were. He, of course, was started introducing me to paleoclimate, and he would pull books off his bookshelf, and he also suggested, why don't you take a class with Hal Borns on ice ages? And that really got me hooked. That's when I really began to become enthralled by climate. And one thing I learned in Hal's class was that this is a recent event, uh, but he mentioned that Mount Pinatubo erupted in 1991, and that's associated with the cool summer of 1992. And so this is almost a decade after the event, and I was immediately transported back to my childhood, shivering beside my friend's pool, and we were talking about how it's just been so cold this summer, and we didn't want to swim. And but in addition to that, we went on a number of field trips during that class, and actually, as well as in earth sciences in general, a lot of field trips, number of classes bring students into the field, even if it's just for a day, but to see different outcrops, to see the landscape, wonderful opportunities, both at the Climate Change Institute and the School of Earth and Climate Sciences. And that is all something that I've benefited from. But going on field trips with Hal, which often also included Dave Smith, and so we would learn about the landscape, the glacial history, and we'd learn about the history, what people were doing at certain times. Another little tidbit that I learned was that Ohio Street in Bangor is named after the exodus of farmers out of the region after the year 1816, year without summer. Well, I grew up just off of Ohio Street, and I had no idea that there was that fascinating history. And I also learned about 1816, a year without summer. And then as I began to learn more about the glaciation of North America and the problem of ice ages, trying to understand why they happened, that really drew me in. And that led to me pursuing a master's. And George Denton was my primary advisor for that. And then so at that time, I was doing glaciological modeling, and I was using the University of Maine ice sheet model, which was developed by Professor James Fastook in computer science, who retired somewhat recently. And he had been working with Terry Hughes, a well-known glaciologist, and Terry passed away, I believe it was in 2017. Peter Coons was my primary advisor for my PhD. Both my master's and PhD utilized the UMaine ice sheet model, and I was studying different paleoclimate problems, mostly focused on the Laurentide ice sheet. My dissertation was focused on reconstructing the last 100,000-year glacial cycle over North America. Now, I won't go into the details of these studies or the results, but I do want to say thank you to my committee members, my mentors, some of whom are in the room. So Peter, I believe, is online. George Denton, Brenda Hall, Terry Hughes, who of course has passed away. James Fastook, who I mentioned, but also Fei Chai, who used to be in School of Marine Sciences. They all, along the way, pursuing my master's and PhD, helped me tremendously. And now, in addition, I'd like to thank Brenda for one. Now, 23 years ago, I had this amazing opportunity to assist in the field in the dry valleys of Antarctica. And this was on NSF grant that Brenda led. And it was a truly amazing experience and further helped me to want to pursue um, uh, academics in climate research. And also, I had the opportunity to work with Aaron Aaron Putnam in the Wind River Range, Wyoming, in the summers of 2008 and 2009. Now, my primary association with that project was running glaciological models using the UMaine ice sheet model to reconstruct the Wind River ice cap. But there were funds that were available for me to participate in the sample collection, ultimately for beryllium-10 age dating. And so I learned how your foot can go numb when you make those charges go off. I must admit, I did not like that part. And I should have made that image there a little bigger. Stop private property. Trespassers will be shot. There was a particular area we wanted to go to. It was a ranch, and I think the original plan was to drive up and ask permission, and we saw the sign. And we eventually did get permission to go on the ranch. And the ranch manager, his name was Ty, or was it Ty or Kai? Ty. I asked him about the sign, and I asked him, so did you ever shoot anyone? And he goes, well, I never shot anyone, but I shot at people. So I guess the dangers of field work, a little more dangerous than working on the computer. So now moving on, after or towards the end of my PhD, I figured it was time to leave, to go somewhere else, experience different things. And so I did apply to a number of postdocs. And I interviewed, but I was not successful in that attempt, although I think I got to number 2 on one that I was really hoping for. Meanwhile, I knew there was a climate modeling postdoctoral fellowship available at UMaine that was open, and I did not apply for it. Even though I was interested in it, I figured it's probably time that they're not going to want me to stay here. I've got to leave. Well, so I ended up approaching Paul Miewski, and I said I'd be interested in applying, and Paul explained to me how they had a number of applicants, and they did some number of interviews. And Kirk, were offers made? Offers were made.
No, Paul and I had a discussion to decide we should have to do if you had to stay.
Okay. Well, and so I was hired for that position,
He
and
actually left it up to me to make the decision.
thank you. I didn't know that. I'm sorry. Thank you. And so the skills I had developed using the University of Maine ice sheet model along the way, doing a lot of coding, that was very nicely transferable to using the weather research and forecasting model and conducting simulations, taking inputs from reanalysis or forecast models, using this model called WRF to produce higher resolution simulations, and also to run sensitivity tests and to simulate future climate conditions for different regions. And so that's what the postdoctoral fellowship was focused on. Now, early on in the postdoc, though, is when I started developing Climate Reanalyzer. And Paul had been, I would say, a little frustrated for a time with not being able to access ERA interim, a type of reanalysis product for which we can see temperature, precipitation, wind worldwide historically from these reanalysis products. At the time, there wasn't an easy online way to get it aside from downloading the raw output files and writing a script and to make the graphics. But Paul had colleagues at the British Antarctic Survey who had a software developer who developed an internal way to access ERA interim. We had a research group meeting in Cambridge, and Paul invited me to come along. It was at that meeting that Paul said, do you think you would be able to make an interface for CCI to access the area term like what is here at the Antarctic Survey? And I said, yeah, I could try that. Because I knew how to make a basic web page, and I had the programming skills that were needed. And the image in the top right is a slide from just a heads up. I'm working on this at the Born Symposium in 2012. And this was literally 2 weeks after I started working on the code. And then the screen just below that is a screenshot from Internet Archive. And I grabbed this a couple days ago, but that was from July of 2013, just the front page. So in about a year's time, the page was online and had a number of, it had a growing amount of content. It's much bigger now and much better known, but it started in 2012. And it really started in late 2011 at that meeting. And so after finishing the postdoc, I then joined the research faculty, soft-funded, in the phase of writing a lot of grant proposals, getting on every project that I could, working with a lot of people, and helping, had to raise salary. And in 2015, I also, in addition to CCI, I started a joint appointment with the School of Earth and Climate Sciences. And then it was in 2021, late 2021 is when I started this joint appointment, 70% CCI and 30% with cooperative extension. Now, also in 2015, George Jacobson is previous state climatologist, and upon retirement, George recommended that I take the state climatologist title and continue that work. And so, George, thank you for passing the baton, so to speak. And so I've been the main state climatologist since then. And so now we're up to what I do currently in my position. With the Climate Change Institute, my role is, of course, as a climate researcher. And my primary interest is large-scale climate variability, especially in the North Atlantic and Arctic regions, and North Atlantic also including the Northeast. And I mean, I've been on a number of projects that have a global scope as well, but my particular interest is North Atlantic and Northeast, including patterns of variability such as North Atlantic oscillation and coupling sea surface temperatures, as well as teleconnections to the El Nino Southern Oscillation. I'm currently a primary advisor for 3 graduate students. Anna Treba presented earlier on an analysis of historical storm climatologies, so we can better understand how historically Maine has been impacted by cold season cyclones. And this is part of a project funded through an NSF EPSCoR grant that's focused on electrical grid resiliency. And as part of that, peering into the future, what can we expect? And the University of Maine has a new partnership with the Air Force weather program. And Kirk is also involved in this. We are advising students on AI machine learning to downscale forecasting analysis. Now, Kirk and I are both learning. The students have made tremendous progress, and it's a Python-based system in which we're able to train with a high-resolution data set, and then apply that to a coarse resolution, either a weather forecast or reanalysis, and then be able to use the AI and to produce the forecast efficiently using a GPU. And so, for example, this is much faster and less resource intensive than the WRF model that I mentioned earlier. And I'm currently teaching a WRF class for several students. But anyway, so that's a bit of what my current students are doing. I'm also on a number of thesis committees as well.
We have a new Air Force guy coming in fall.
Yes, yep, absolutely. And there'll be a 1 semester overlap with our current Air Force students, which will be really nice. As Maine State climatologist, I provide climate services, and that entails the production and translation of climate and weather information for stakeholders. And so that can be pretty broad. There's many different things that state climatologists do. And this is to facilitate decision making and planning. And so I communicate with the National Weather Service, with Maine Forest Service, and when Maine is in a drought, I also am on the communicate with the drought task force. And since fall 2019, I have been serving on the Maine Climate Council's Science and Technical Subcommittee. For those of you who may not be aware, the Maine Climate Council was established in 2019 through bipartisan legislation, and its ultimate goal is to develop Maine's climate action plan. And the initial plan was developed in 2020, and then a follow-up plan was also released in 2024. So it's the state's means to adapt and mitigate in the face of climate change. And the role of the Science and Technical Subcommittee is to provide the baseline climate. So on that note, I've been involved in a number of reports, including the Maine Climate Futures Maine's Climate Future Series reports that was initiated before I was involved in this in 2008. And George Jacobson was heavily involved in that, as was Ivan Fernandez. And I know, Kirk, you were involved, and many other people in the Institute. It was a really large Institute effort, especially that report that came out in the 2008-2009 timeframe. I was later involved in update reports in 2015 and 2020. And then the Climate Council STS produced reports in 2020, 2024. And we have a brief update report being released on Earth Day coming right up. And now I am being mindful of time, trying to be mindful of time here. I want to mention a recent project that many of you are aware of, some may not be. University of Maine received congressional funding to build a new statewide 26-station weather observation network across the state. And this is in support of agriculture, forestry, and other stakeholders, but primarily agriculture and forestry. These 26 stations will be in either 10-meter tower configurations, such as shown there. We also have a few that will be 3-meter tripods. They'll each have the common mineralogical measurements, temperature, precipitation, wind, but also soil temperature and moisture probes down to 50 centimeters. And so this will help facilitate weather-based decision products for agriculture and forestry, help in terms of fire weather monitoring, especially with the surface and subsurface probes, as well as fill observational gaps. And all the data are being fed into the National Weather Service, where they can utilize those observations and can be incorporated into their data products and forecasts. And in addition to that, other stakeholders include recreation, emergency management. And so we're really excited about this project. And as you can see, the team listed there, Devin Roper is in the audience, is our MESNet manager, who has been hired full-time to lead the setup of the instruments, and is also recently became affiliated with the Climate Change Institute. So now we're going to pivot a little bit, having gone through the bit of my background and what I do now in my current position. So we're going to change this a little bit and start focusing on Maine's historical climate. Now, ordinarily, I would talk about temperature, precipitation, incidents of storm and heavy rainfall. But to get to this interesting story of these historical freeze events, we'll focus on temperature. Over the last century, from statewide records that are available and have been compiled by NOAA beginning 1895, there are older data, but the consistent records begin 1895. Maine's climate has warmed by about 3.5 degrees Fahrenheit since 1895. 10 warmest years have occurred since 1998. And when we project into the future using climate models, depending on greenhouse gas emission scenario, the warming could be anywhere from 2 to 10 degrees Fahrenheit. Now, to boil this down in terms of how does it impact the winter season, and now getting into, if you look on the left side, those big dips in the early 1900s. That's when the bay would freeze. And now I said that the overall warming has been about 3.5 degrees Fahrenheit, which you might say, well, it doesn't sound like much. And perhaps it doesn't sound like much, but when we look at the temperature annual cycle, as shown here, for 3 different climatologies, this is 1901 to 2000. Excuse me. I think I'm talking too fast. So the blue line is a 100-year climate average for temperature every month of the year. The orange line is for the 2010 to 2023, a more recent climatology, and the dark red line is for projected to about 2050. And the key point here is that you can see how these curves shift with each step. And then dashed in the 32 degree Fahrenheit, the melting freezing line. Now, if you look at that and compare these curves, you see that there has been about a 2-week relative lengthening of the warm season, and likewise a shortening of the winter season in terms of temperature. And now, also, we can think of the accumulation of freezing degrees. In this warming climate, there are fewer freezing degrees and a shorter season, and so that inherently impacts the cover of snow and ice. Shorter duration, and for ice, both on lakes and in elsewhere, there's just less opportunity for ice to get thick, or in some cases to form. So now here is the Coastal Climate Division November through March temperature signal. And these events in the early 1900s, with the last one being 1934, those all have really good historical information, in many of those years photographs as well, of a frozen Penobscot Bay. Now, there were some moderate freeze events in 1948, 59, and 1971, which the upper portion of the bay froze. But nothing quite like it has occurred since, although in 94, 2003, and 2015, there was also a moderate freeze, and I know Portland Harbor froze those years. The upper part of Penobscot, I think down to about Bucksport froze. And then to put this past year in relation to the previous, it felt like a real winter. And but here's 2025. That would have been perhaps a moderate year a century ago. Okay, so here's the focus area, Penobscot Bay region. And in this expanded view, I have placed dashed lines to where, from the information that I've read, photos that I've found, other documentation, that's about where it seems the ice edge would extend during these big freeze events. And including in Frenchman Bay. And again, this was beyond Penobscot Bay, but this is focus. Now I'll step through this fairly quickly. I've added in some historical photographs of the era just to help us place in time. So 1934, that was the last time the Penobscot Bay froze to a great extent, all the way down to Rockland. Franklin Delano Roosevelt had just become president at that time. And here's a couple examples of newspaper clippings. This is from February 12, 1934, New York Times. Record ice blocks New England coast. Skating on frozen harbors and menacing drift of flows mark cold spell. And there's even a mention of Penobscot Bay. A solid sheet of ice 30 miles square and a foot thick covers Penobscot Bay in Maine. The Coast Guard cutters Kickapoo and Ossipee are trying to break channels into the bay ports. And in 2015, that was the last really pretty substantially cold winter. In February 2015, the Bangor Daily posted articles recounting the 1934 freeze event. And this quote, "It froze all the way across the Vinyl Haven," he said. "Friends of mine went on the ice outside Owl's Head." So that's a good indicator. That's really far south down the bay. "Ice was going up and down. It just doesn't sound like anything you want to do." Now, I learned something. The box is highlighting the between Stonington and Isle Ho. I had shown a couple of these pictures when I gave a presentation to the Maine Maritime Museum in Brunswick. And a gentleman came up to me after the talk and he said that he was a retired merchant marine and that, as he put it, in his youth in the 1960s, I was talking with the ferryboat captain who worked out of Stonington. And he told me about how in 1934, the ice was so bad that he couldn't run his boat, but he could walk from Stonington to Isle Ho. And that's about a little over 5 mile trek. And I later learned that the Isle Ho Historical Society has photographs of that event. Now, going back a little bit more, this is the winter of 1922-23. This photograph, I found this on the Maine Memory Network. Lieutenant Commander McMillan of the Bodenham Arctic Expeditions. The Bodenham, I believe, is now kept at Castine at the Maine Maritime Academy. General A. Greeley, he fought for the Union. And Hiram P. Maxim was a famous inventor, and his father was also perhaps a more famous inventor. And then Governor Percival Baxter on the right of Baxter State Park fame. So in this freeze, here's a view. There's Great Harbor just south of Somme Sound, and Great Harbor would sometimes freeze as well. And so this account shows Branscome's Coal Wharf. And so the camera is looking pretty much up towards Branscome's and more or less towards the northwest. Coal and Wood Wharf in the winter of 1923, the last year, all of Somme Sound and the Great Harbor froze over, making it possible to walk to Islesford. And so for now, we'll take that at face value. I don't know if maybe it froze in 1934 as well, but perhaps it didn't. At least not that area. Going back another step, and I just want to check, how much more time do I have?
Until 2:15 you have?
Yeah.
Oh, is it till?
Because you got 10 minutes extra at the beginning.
20 minutes.
Oh, I have a captive audience. Great. I'll get all kinds of slides. Okay, good. We'll get through all the cool stuff. So 1917-18. This, of course, was during World War I, getting towards the end of the First World War. And this photograph in the upper right is from November 11th. That was Armistice Day. And one thing, it's easy to remember that because it was the 11th hour of the 11th day of the 11th month of 1918 that the armistice was called. And that gentleman has fashioned the bullhorn, and he's calling out in Skowhegan, letting everyone know the war's over. And the image in the bottom right, Boothbay Harbor, and you can see the pier heavily coated in the pilings coated in ice. And just beyond the pier is a schooner that you can see locked in the ice. Here is Carver's Harbor, Vinyl Haven in February 1918. I should note that these freeze events, typically they would start in January, and then by February is when things would really become entrenched. And the breakup would typically be in early to mid-March. And some of the harbors wouldn't break until April. Belfast Harbor, for example, I found a couple references to it not breaking until the first part of April. Now, this is actually the photograph, the first one I saw. And in this account here, this is the very first one I saw about the bay being frozen. And I had been searching for snow and ice cover. At the time, I was trying to find information about late lasting snow on Katahdin, as well as Mount Washington. I was really curious about that. But instead, I somehow stumbled upon this antique auto website. And it was on there because this was a Ford Pathfinder that had traveled across the bay pulling that sledge laden with supplies. And the person who posted that, they spoke to a relative of someone who owned this Pathfinder, and that person who owned it was Captain Albert Gray of Harborside. And he ended up posting the story on the antique car site with this quote from the Bangor Daily News from February of 1918. I'll read a part of this. February 24, Belfast. Automobiling across the bay from Brooksville and the Castine has come to be a regular thing now. The Pathfinder Ford, which made history Friday by being the first car to cross the bay on ice, made 4 trips Saturday to Brooksville, towing a horse sled loaded with over a ton of grain and provisions and making the 12 miles across in about 25 minutes. The car took to the ice at Goose Falls or Harborside and same across to Turtle Head, up to Belfast Harbor. Other cars came over Sunday and Penobscot Bay turned into something of a boulevard. And a few days later, this is also in the Bangor Daily. This is from March 1st. Now, I'll mention University of Maine Folger Library provides access to some newspapers, including the archive for Bangor Daily, perhaps also Portland Press Herald. And we also have access to New York Times and the Times Machine. And it's a great way to get at this historical information that's in newspapers. So I mentioned this one because this follow-up article had a few more details, one which really piqued my attention. Okay, so much for the pioneer trip of the Ford or any other car on the ice-bound Penobscot. When S.D. Gray, these boys' grandfather, crossed the ice 43 years ago, such that a thing as an automobile was unheard of. And when next the bay was frozen 13 and 14 years ago, there were no cars owned either. So 13 and 14 years earlier, that refers to the winters of 1904 and 05. 43 years earlier refers to 1875.
Krakatoa.
Krakatoa was 1883. Oh, no worries. And I will mention another volcano very soon. And so I do wonder the impact of Krakatoa, and I have been very interested to see what the impacts might have been, but I haven't found a specific reference to a freezing after that event. And so the 1875 event, I haven't found any photographs of it yet. I did find a photograph of the upper portion of around Penobscot Narrows between Verona Island and mainland, chock full of ice and a steamer locked in. That was 1872. But so there was this 1875 event, and I'm still searching to try to verify that. And here again is a quote from the 2015 Bangor Daily News article recounting some of these freeze events. This one for the 1918 event. So this is from Barbara Dyer, a 90-year-old Camden historian from Camden. And she said that as a teenager in 1916 or so, 1916 was a warm winter. And so I can say with pretty much absolute certainty, this was 1918. Her father took advantage of the deep freeze that turned open water into ice. He lived on Islesboro and he walked on the ice from Islesboro to Belfast and from Islesboro to Camden. She said, I suppose he had places to go and he wanted to get there. Now, at talks that I've given, a number of people, because I've given talks at retirement communities, and a number of people said, my grandfather told me about used to walk across to Islesboro, and so there's still some living memory of the 1934 event, and then there's still living memory through one step back from some people. 1904 and 05. So just to clarify, the 1904, that'd be the winter that starts at the end of 1903 and ends in 1904. Likewise, the next one would be 1904-05. But there were 2 big freeze events, one year after the other. In this one, there's pretty good evidence that this is probably has an association to the eruption of Mount Santa Maria in 1902. And I can get into why these major explosive eruptions have an impact on the North Atlantic Oscillation and the way the jet stream shifts tends to produce a cold winter in the Northeast region for a couple of years after a big eruption. Now, so these photographs, these are from postcards. Postcards have been scanned, but they're from black and white photographs that were colorized. And the top one shows is looking south towards Belfast, and the bottom photograph is Bangor's on the right, Brewer's on the left, and we're looking south. And this is a lumber raft, circa 1905. You can see lumber schooners over on the side, and I have one more photo here, also from around 1905. Here's a lumber schooner, and you can see the lumber right there. And so Sea Dog would be somewhere over, if you were to go down there today, the Sea Dog Brewery should be somewhere around here. And probably can't see it, but in the distance there are boxcars. This was also nearby the old Maine Central Union Station. Okay, so now we're 1905, February 6th. This is in the Telegraph, a British newspaper. Southern New England harbors are impassable. Nantucket isolated. Embargo at other Atlantic coast ports. I learned from reading these articles that up until 1934, the terminology ice embargo was pretty common, at least during these big freeze events. And I had, after 1934, I did not find that same term. This article here, Chesapeake Bay blocked. Only biggest steamers can get through the ice. And this one over here, ice blocks the sound. At Long Island Sound. Not in 20 years has the ice on Long Island Sound been so thick and steamboat traffic so completely tied up. Kirk and I, a couple of years ago, gave a Climate on Tap, and Kirk showed a lot of photographs from Long Island Sound and from that region, and I showed some of these slides. From
My grandmother told me stories about people driving cars across the Sound in 1934.
Yeah, that's amazing. This is a photograph from Belfast Harbor. The winter of 1905 was hard, but not as hard as the winter before. Temperatures seldom rose above 12 degrees Fahrenheit. Now, I checked that out. That's a little bit of an embellishment. For about 2 months, temperatures didn't get above freezing, and it was getting really cold, getting 0 and sub-zero mornings. But there were days that got well into the teens, into the low 20s, because there are data from Belfast. We can also look at records from Bangor. So we could actually calculate how many freezing degrees is required for the ice to form. It does say much of the upper Penobscot Bay was frozen solid with 5 inches or more of ice. Steamboat travel was suspended. Newspaper reports beginning mid-February told of people walking from Castine to Belfast and of an ice bridge. So again, this is one of the freeze events that was referenced in the article from 1918 as well. And here's the revenue cutter Levi Woodbury with the ice 15 inches thick in Belfast Harbor. That was winter of 1904-05. And so you can see this saw. They're trying to cut an ice for the ship. I mean, surely they were a little scared they might fall through.
Ice floats. Ice floats.
That's true. And this one is just for fun. Going through these old newspaper articles, you never know what you'll find. And this is from February 1905. And the headline really caught my attention. Miser of Cherry Hill dies at the age of 107. Well, okay, I'll read that. Crowley might still be alive except for his snow shoveling. Andrew Crowley, who lived at 69 Montgomery Street, just around the corner of Cherry Street, is dead, and last night his friends had awakened, as befitted a man who had lived 107 years on this earth, and most of them in that locality. Now I'm going to skip down a little bit. The neighborhood didn't join in waking Crowley. Gathering at O'Donnell's and other places nearby, they told stories about the old man who came to his death at last because he wouldn't hire a shoveler to clean the snow out of his backyard, but insisted on doing it himself. This despite the fact that he owned his house and another more or less like it around the corner in Cherry Street. The neighbors deemed him a miser, and misers are not popular in Cherry Street.
I can see why they didn't want to wake him. He might come back.
Being 107 and even contemplating shoveling that is really remarkable. I think I would have paid someone to shovel though.
But not if you were a miser.
Right. So now the final couple stories that I want to relay. This is the document, you saw this towards the beginning. History of Castine, Penobscot, and Pennagoet, Maine, including the ancient settlement of Pennagoet, published 1875. These documents are, of course, digitized, and with digitized documents, you can do keyword searches. So I was searching for snow, ice, frozen, and I came upon this. Penobscot Bay. I found that Penobscot Bay froze 3 winters in a row in the early 1800s. Since the incorporation of Castine, so either 1787 or 1796, Penobscot Bay has been frozen over so as to permit passage to Belfast upon the ice some 4 or 5 times only. Important information. The first 3 times in which this event occurred were the 3 consecutive years of 1815, 16, and 17. And now in other parts of this document, I was able to confirm that 1815 is referring to the 1815-16 winter. And the 16 is the 15. Yeah, so 15, 16, 16, 17, 17, and so on. After the eruption of Mount Tambora. And many of us have heard of 1800 and froze to death. The year 1816, year without summer. Now, in truth, there were some warm days, but that summer was punctuated by killing frosts across parts of New England into late June, then again in late August and mid-September. And so crops were ruined, and not enough food could be produced. So there was really serious concern of hunger. Snowfall as far south as Connecticut on June 7th of 1816. August frost reached as far south as North Carolina in August. Failed crops across New England and in parts of Europe as well. And this is now pretty well understood to be associated with the eruption of Mount Tambora in 1815 for how an explosive volcanic eruption that puts sulfur dioxide into the stratosphere produces an aerosol cloud, and low latitude eruptions that do this. The material can spread across both hemispheres and cause a global cooling that's temporary. And Tambora was the largest volcanic eruption in recorded history. And for comparison, Mount Pinatubo of 1991 was an order of magnitude smaller, and that caused a temporary cooling as well. Now, there happens to be temperature data, daily min-max observations from Dennisville, and it starts in early 1816. And so it's interesting to look at that record. It looks like the winter of 1818 was actually the coldest, and there were 3 mornings that got below -30 Fahrenheit. Dennisville is near Eastport, so it's on the Maine coast. And those are the kind of temperatures you might still get up in Caribou, Fort Kent. So these are really cold air masses. Yeah, so there's the present day caldera of Tambora. Okay, so now this is the last example, and then I will release the captive audience. Penobscot Bay froze in the winter of 1780 to 81 during the American Revolution. On October 27th, 1780, there was a total eclipse of the sun. There were stories about this in the news a couple of years ago when there was the eclipse in April. And so at that time, there was a war going on. And the researchers from Harvard who wanted to make observations because they had estimated that the Castine area would be ideal for capturing the full effects of the total eclipse. The British officer in command here refused to allow his party to land upon this peninsula and only allowed them until the 28th to remain at the bay. And now I mention that because this is 1780. Now the next part continues. The winter of this year was probably the coldest ever known in this vicinity. The cold was so intense and for so long a period that the bay was frozen over from here to Camden, and Lieutenant Burton, British soldier, came all the way from that place on the ice. He was in search of a man by the name of Libby, who was imprisoned here at the time. After obtaining his release, Burton returned with him in the same manner. So this is during the American Revolution. A British soldier walks across bay, gets an American prisoner, and brings him back. And then I found confirmation of that event, or at least another telling of it, in this book, An Islesboro Sketch, published in 1890. I was also able to find, I also found another document that discussed Burton and Libby's, but it wasn't talking about the bay, but it was just a history of the conflict. So now this section here, Old Shauble Williams. And Shauble Williams is understood to be the first European settler on Islesboro. And his farm site is it's well known. There's a plaque, and you'll see a map of it shortly. Old Shauble Williams, of revolutionary memory, selected his farm on a lovely spot in the center of the island, where two pairs of indenting bays have almost bisected the island and enclosed it. Now it continues on. After the old man had suffered for his sturdy patriotism, the islanders were pretty much forced to become neutral by the British. They're more or less given an ultimatum. So after he had suffered for his sturdy patriotism, his pretty daughter became enamored of a British soldier at Castine. And he used to cross the bay to meet her clandestinely, but unfortunately he came once too often. Upon a cold night, he skated over the ice, guided by a light in the cottage window, but just before reaching the shore, he fell through an air hole and was drowned. The father was not very sorry, but the daughter grieved sadly. Time, however, is the greatest author of grief. She afterwards married another. So here's
the father made the air hole.
Maybe
Put the light there.
he must have known that guy's coming at night. So here's a map of the bay, upper portion of the bay, and there's Castine. From Castine Harbor, it's a straight shot to the Shauble farm, unobstructed. And so obviously 6 miles out, you wouldn't see the candle in the window, but as you approached, so it's entirely plausible. And then I also dotted out the line Camden to Castine that the British soldier may have taken. Now, perhaps he went across to Islesboro and stayed along the shore. I don't know, but regardless, it's approximately 19 miles from Camden to Castine to walk across the ice. It's a pretty big difference. So with that, I would like to thank all of my CCI colleagues, graduate students, and also Dan Churchill for your support for CCI and all the things that we do here. I have worked with so many wonderful people at the Institute over these many years that I've been affiliated with the Institute. So thank you all, and thank you for inviting me to give the alumnus talk. And I hope that you've enjoyed this. And the very last thing, this is a work in progress. If anyone has stories, if you have ideas, I would like to compile a document that synthesizes some of these interesting historical weather events. It could be freeze events, but also major storms, And it's not a funded project, but if anyone is interested in contributing, or if you have personal memories or family memories, I'd also one next step would be to reach out and try to get indigenous knowledge and to find out what may have happened to prior to colonization, stories climate related that could go into a document of this sort. A resource that in the next year or two we could build this up and place on the Climate Office website as a resource for Maine, for the people of Maine. Anyway, so that's, if you have any ideas, please let me know, and thank you very much.
And there's certainly time for questions. Actually, I have a question, sort of a question. Oh, I was always told that Winterport is called Winterport because it was reliably ice-free in the winter in the 19th century when the ships were coming to get the lumber.
Yep.
And that's what, so have you looked at their records? Because any year it was open, the ice didn't get down, and so it certainly didn't get into the bay.
That's, I have not thought of that. And I was aware of Winterport being named for that reason, but I hadn't thought of seeing if there are records from locals in the area. There, I'll have to check to see. I don't know if there's a Winterport Historical Society or.
We can look.
Yeah.
You can ask Gretchen Faulkner because she's lived in Winterport for a long time, and she's a historical archaeologist to be attuned to these things.
Okay, great. Yeah, because I found a couple photographs taken from right nearby in Bucksport. I was thinking about trying to find maybe a Bucksport Historical Society. So this is kind of a side project, and so I don't really have a whole lot of time. There are several different historical societies I'd like to reach out to, and I did have a student, Max Valentine, 2 summers ago. I had a little bit of funding, and he helped out compile some of this material, and had reached out to a couple of the historical societies, but I hadn't thought of Winterport. Glad you bring that up. Yes.
Region, but have you found out any information like further down east, like
Yes.
far back, further than like Acadian Bar Harbor?
Well, this photo here is from Frenchman Bay, stuck in the ice right off Bar Harbor, and this is from 1880. Circa 1880. It was also that one of the first photographs I showed was from just outside of Lubec.
The Dennisville record goes way back.
Yeah. Yeah, the Dennisville record begins early 1816. Yeah. And also Casco Bay, freeze events in that area, including so people could walk to Chebeak Island. And there's a really good record of Portland Harbor, years that Portland Harbor froze.
There's the Portland record from Munjoy Hill that goes back to the early 1800s as well. Unfortunately, 1816 is missing. Someone must have borrowed it and not brought it back.
They moved to Ohio. Huh. Yes.
Well, I'll explain why I'm asking this question in a minute, but what do you think the temperature would have been on top of the ice sheet here at the LGM?
Probably comparable to on the Greenland ice sheet. And so in the middle of summer, 10 degrees below freezing, just making a guess, but it's hard to say exactly where the ablation zone was. And then of course, when, let's see, when Katahdin was a Nunatak, was that surface all in ablation? Maybe it got above freezing in the summertime, or when it was at its maximum extent. Then
The winter temperatures would have been, let's say at Katahdin at the LGM.
I would surmise probably Baffin Island today atop the Barnes ice cap or Greenland would at least be reasonable estimates, just given, especially the Greenland ice sheet, given the topography, in that more or less the climate that's supporting the Greenland ice sheet that sort of climate would have been necessary to support a low extended far to the south of Laurentide. Now there are the climate model estimates for the LGM, and could take a look at that too. I have some of those model results from CCSM4 I could take a look at.
Now I'll tell you why I asked.
Sure.
In 2009, I was the
Oh,
state climatologist I retired from the university in 2008, and Paul talked me into becoming the state climatologist, which I did for 6 years before Sean came along. To do a much greater record job than I did. But anyway, in 2009, on January 16th, I got a phone call from one of the weather service up in Caribou from a guy who said, George, we just had a reading of minus 50 degrees on a sensor up in northern, west of here. And if that's true, it's a all-time state record. And we have to investigate it, and you're on the committee. And I said, yeah. It turned out there's an official way to decide if it's an official state record or not. And that involves weather service people, the state climatologists, and people from the National Climate Data Center in Asheville, and a few other things. And so we had a conference call and had a discussion, and it turned out that everything looked good. The temperatures in some nearby areas had also been about the same, so it wasn't some kind of anomaly in the data. And then somebody asked the question whether the equipment, which was a USGS sensor on a weir on a river, which only was interested in when it was melting. They didn't really care about how cold it was in the winter. They wanted to know when the spring floods were coming. But was that sensor rated to minus 50? The answer was no, only 40. So there had to be a study done. So the company that made the thing provided 3 more units just like it, new ones, and they were sent to the National Cold Testing Center to be tested. Where do you think that was? Mississippi. Some senator, I know which senator it was, made sure that was in his state. So anyway, they were sent down there. It turned out to be that they all worked fine to minus 50. So it was certified as the state record. So then I got a call saying, well, we have to have a press conference. And I said, press conference. He said, yeah, this is people are so interested in this. And they aren't interested in global warming or anything like that, but a cold night in Maine. So we met in Augusta at the USGS offices here, and we planned out the thing. And I was going last to give some historical perspective. So a young woman from the USGS who was responsible for the instrument in the field spoke, and then went like that, and then it was my turn. And I got up and said, well, this probably isn't the coldest it's ever been in the state of Maine. I said, it's probably a lot colder at the peak of the last ice age. Well, I thought it was kind of a funny thing to say. I just got stares. So that wasn't very successful. So anyway, I explained that it actually was interesting because the previous record was from Van Buren.
Van Buren, 48.
1925. It was a long record. So it was, a long interval. So anyway, so I went home and thought that was the end of it. The next day I got a call from my wife's sister who lives on Cape Cod and said, George's picture is on the front page of the Cape Cod News. So there's somebody taking a picture of me while I was talking about the last ice age. And so it was on there. So I called up the head of the weather office in Caribou and said, I'm really sorry. This should have been one of you that was in the photograph. I had nothing to do with it. He said, oh, it's okay. It's been great. We're getting all kinds of coverage. He said it's been in the papers all over the country, in Los Angeles and Miguel, India. So that story, I mean, it was just so interesting how that captured people's imagination.
Yeah,
it's so interesting.
Just a few weeks ago, I was thinking about that record that you had worked on, because the National Weather Service, a fairly new employee, had written a weather summary for I think must have been for March, and listing that the coldest observation was -46. I was like, whoa. So I checked the surrounding stations and nothing was colder than -20. It was actually the apparent temperature. But I sent an email and I said, I think this should have been the apparent temperature. And I mentioned the statewide record. I said, that's pretty close to the 2009 record. But yeah.
Thank you very much. It's great.
Thank you.
So we have two more things to do as we wrap up the 2026 Born Symposium. The first is to go through the plenary of graduate student presentations, which I'm going to do now. And then please don't leave because we will then give out the awards. Now, is there anybody left on Zoom?
I'm here, but that's okay.
I'm not sure how to connect. Well, you can hear me, but you won't be able to see, but you can hear
That's
it.
okay.
All right. All right. So Warren's Plenary 2026. Start with yesterday's. They're going to go in the order of presentation. I don't want to say that I don't punerize the COP papers or the COP papers. I guess you could say that I copped out. But I will note that Belém, where the COP 30 was held, where the 5 people went, has the same root word as Bedlam. Who knows? Anybody know what that root word is? Bethlehem, yes. And Bedlam comes from a local name for the London Lunatic Asylum, formerly known as the Hospital of St. Mary of Bethlehem. So that's where we get Bedlam from. So I give you that one factoid related to the COP meeting. And I'll start with the talks. Our first was Elizabeth Rogers, who spoke on holding space for eroded landscapes and indigenous cultural places, a view from the Holmes Point West site in Passamaquoddy homelands. The site is suffering from a disappearing act. This is a risky business that archaeologists need to take into account. At Holmes Point West, what you see may be what you get, but it isn't everything that was once there. Appropriately fixing the broken links between indigenous communities and their past is essential, if difficult. Kenzie Anderson presented archaeological investigations of the material culture of the Little Ice Age from Long Point Preserve, Machias, Maine. Kenzie pointed out that some cool Little Ice Age material culture still preserved at the site. This is the Long Point Preserve, right, where she works. As someone who has long studied archaeological mollusks, I selfishly want to note that Kenzie's work was at a shell heap, although she focused on other fauna, lithics, and ceramics. Lithics and ceramics, stoned and potted. Renee Clavette gave a talk about ice thickness estimates across the Juneau ice field from ground-penetrating radar surveys. Renee addressed the question of how thick the Juneau ice field actually is, which made me think of Jethro Tull, and if you're not my age, you probably won't get that. She discussed good and bad radargrams, and paradoxically, it's the good ones that can give the bad news that the ice is thinning. Renee also noted that local radio stations are interfering with results, and to follow up on my previous pop song reference, she can hope that video kills the radio signal. Mike Goodwin told us about investigating global synchrony, the S mark of the South, question mark. He argued that one would have to be spaced out to think that orbital cycles fully explain climate shifts. Using data from his work in New Zealand, Mike connects the Whale Stream moraine to moraines elsewhere. And the Whale Stream record is not a fluke. This supports hypotheses about non-orbital drivers of global synchrony. It's sort of a kumbaya moment for the Antarctic cold reversal. And we'll come back to that. Pradama Pahadi's talk on how do large-scale climatic gradients influence coordination among leaf economic spectrum traits across tree species shifted our thinking about arboreal responses to climate change. She noted that climate is changing faster than trees can adapt or migrate. In other words, climate change's bite is worse than its bark, especially for trees. After explaining leaf economic spectrum, she branched off into a discussion of an experimental study of tree responses in different parts of Maine under different conditions. Avery Lamb explained how she uses integrated paleolimnological proxies to reconstruct 150 years of genus-specific cyanohab responses to seasonal temperatures. The core of her presentation was about how cyanohab taxa varied according to climate conditions through time and across seasons, and she studied this in part from looking at cores. Seasoning may not make these toxic taxa more palatable, but they do explain abundance of taxa, though differently by species. Andrea Terrell scaled new rhetorical heights to tell us about alpine plant communities of Katahdin, resilience and change after 33 years of climate change and recreational visitation. I'll say this for one of the last talks, but one of my graduate advisors, Art Bloom, a geomorphologist and an honorary degree earner here at the University of Maine for defining the Penobscot Formation, used to say that archaeologists wrote titles that were abstracts, and I would say it's not just the archaeologists. There are a lot of titles here that are basically abstracts. All right. So Andrea used the marginal cost of alpine species survival. Discussed the marginal cost of alpine species survival. We're all familiar with how humans use plants to get high, but Andrea is working on how plants themselves manage to get high or survive them. By comparing her work with a 1989 survey of Katahdin alpine plants, she showed the up and down effects of ongoing climate change. Xander Roman spoke on Little Ice Age glacial advances found in the southern Alps of New Zealand at 43 degrees south, suggesting a global extent. He used inductive reasoning, studying local to think global, in advancing our understanding of the Little Ice Age. Little Ice Age understanding is no small accomplishment. His data also argues for a climatic kumbaya moment in the Little Ice Age. Xander's bolder assertions support volcanic and solar variability hypotheses for global synchronicity. And to end up yesterday, Catherine Westbrook spoke on re-advance of the Scandinavian ice sheet during the Antarctic cold reversal. She afforded us a new view of global climatic synchronicity from Norway and New Zealand. And since repetition is a common comic trope, and I used to study comedy, seriously, I'll point out that this is another kumbaya moment for the ACR. The big question is, who's in the driver's seat? Moving to today, we started with Emily Blackwood, who suggested that we should get visual on the north coast of Peru, or as mistakenly said originally, get physical on the north coast of Peru. Well, I can see the value of her research on visualization at the Ostra Collecting Station. Her ideas about the value of these 3D reconstructions are anything but half-baked. Remember, she's working on oysters. She threw out some interesting hypotheses about the sling stones, in which she did get physicsal, because she gave us the physics of throwing sling stones. Well, she still has some details to hash out about the slingers' actions. Hash slingers, right? But this is a great advance. Matilda Borch explained how glacier slope steepens as marine terminating glaciers retreat onto land. She began by showing how many people are at risk from rising sea level, which dampened the mood. Like Emily, Matilda gets visual, using 8 decades of observation of a glacier in Greenland to study the effects of glacial transition. Paradoxically, she then explained that retreat leads to rise. That is, glacial retreat from marine to land termination pushes sea level rise. Morgan Anderson talked about reconstructing Holocene seabird colony dynamics in the Gulf of Maine using guano geochemistry. Thank you, Morgan, for giving me some good openings. I suspect that Morgan takes a lot of crap when people hear what she studies. But using guano to figure out when birds were in the Gulf of Maine is not a bird-brained idea. It was fascinating to get the straight poop on what Morgan has found so far. Elijah Bradshaw spoke on pawpaws and paleoecology in the Southeast U.S. Starting with megafaunal seed dispersal, particularly of pawpaw fruit, Elijah made it clear that he is also talking crap. He did experiments to see if pawpaw trees could have survived in the Pleistocene in their climate niche, which is now in the Southeast, or was then rather in the Southeast, and collected pawpaw fruits in North Carolina. He used these fruits of his labors to apply different treatments, treatments, to the seeds in order to study the effects of digestion and fire on seed viability. Kayla Guthrie assessed recovery from acid deposition in alpine lakes in central Norway. She discussed Noxus and Soxus deposition from anthropogenic sources. This leads to more acidic lakes, which sounds painful and has significant effects on nutrient balance and community composition. Better policy has fortunately led to a decrease in NOx and SOx, NOx and SOx, but Kayla still has core questions about biological recovery that she's studying in cores from 3 Norwegian lakes. Kate Johnson discussed calibrating isotopic analyses of trachycardium shell material as a proxy for ENSO behavior in North Coast Peru. For those who don't know, trachycardium is a cockle, that's that kind of shell. And as a long-time student of ENSO in Peru, this study warms the cockles of my heart. And I've been doing stuff with trachycardium for a long time. Figuring out a proxy for El Nino isn't easy. One might say it's not child's play. But I would be shell-shocked if Kate's work doesn't lead to a valuable ENSO proxy. Matilda Borch came back to tell us about estimating spatial variation of snowmelt to enhance understanding of meltwater and input and storage in the snowpack at Taku Glacier, Juneau Icefield, Alaska, or as she summarized it, where is the water? In other words, she's engaged in wet work, and in her talk, she really slayed. Given that Matilda reminded us that glaciers will disappear, I hesitated to instead say that she iced it. I may be all wet, but I'm still not sure where the water is. Thomas Grindle talked on autumn 2022, anomalous heat and precipitation in West Greenland. He discussed Lake Browning, and just so you know, this is a lake condition, not a lake name. Despite what it sounds like, Browning comes from iron and dissolved carbon, organic carbon, even though he characterizes some of the relevant compounds as aromatic, which makes one think of other kinds of Browning. Thomas studies shallow inland lakes near the Greenland ice sheet, where he did a deep dive, paradoxically, into causes and effects of Browning. Tricia Hall Collins discussed Scandinavian ice sheet behavior during the last deglaciation and the late glacial climate reversal. Despite depending on the dating of erratic boulders, Tricia's data actually argue for climate coherence across hemispheres during the ACR and the YD. This is more evidence for a climatic kumbaya moment. We seem to be getting warmer in terms of nearing an explanation for late glacial ice dynamics. Caleb Manello outlined the evolution of temperate fern under melt conditions in the Juneau ice field. She's clearly very fond of her topic, even though she told us these are not the plant ferns. I'm going to go with that. Her work plants some new ideas about fern evolution. Fern may absorb water and dampen sea level rise as global temperatures rise. Kaylee is now studying how much fern there is and how much water absorption fern can furnish. Despite loss between 2012 and 2021, subsequent surveys show that fern is turning up the volume, but apparently that trend is a slow job. Think about her talk. And Atreba presented an analysis of the December 18, 2023 extratropical cyclone. She took us on a whirlwind tour of this event and its consequences for the electrical grid. This cyclone zapped the Northeast and left it looking like a pigsty, which makes sense since the storm was a southeaster. That's for my bill. High winds meant many people lost power, and this is not a comment on current events in the US. Jacob Holmes spoke about ground truth and direct observations of subglacial hydrology and sediment controls on basal stability at Taku Glacier. He spoke about his plans for upcoming work at this glacier in the Juneau ice field, including the potential role of basal sediment deformation. His planned research, therefore, is both a dirty job and a boring job, because he has to take, but somebody has to do it. Jacob also discussed driving stress and basal resistance, which could also characterize current politics. Leonardo Villasís spoke on recent warming following a century of intense local perturbation and how it drives abrupt shifts in a northern Maine lake. It was hard to come up with a yoke about Leonardo's pond study, but I'll try. He has been attempting to record the environmental effects of the 19th to 20th century yoke pond logging camps. He's logging these things in the environmental context of the last millennium. Leonardo used cores from 2 ponds to drill into this history. He showed a diatom record to dive for. It was a really interesting slide he showed. I particularly appreciate how Leonardo made whoopee. And I mean, of course, he made a whoopie pie metaphor. Don't go somewhere else. Wyatt Stanley gave the final student presentation on combining UAV remote sensing with in situ snow pits and co-located automated weather data to make high spatiotemporal resolution SW estimates. And this might take the prize for the longest title at the Borns. this year, but he does have some competition, as you will recall. Wyatt started with a sweet correlation between SWE and spring melt, and showed that the consequences of high SWE aren't all sweet, since it can lead to flooding, although it also provides more available water. So we need to know more about it. There are problems in studying SWE, since it is highly variable and current methods aren't very precise. Studying SWE is neither sweet nor easy. And with that, I'm going to end that summary of your talks. Good job, students. Thank you, everybody. And we'll move on to the last part of the Bourne's event, which is presenting the awards. I want to thank all of the judges for their hard work in judging the talks, all of the presenters for a lot of really good presentations. It has been suggested that some people could use some better pointers on making slides. All of the science was great. Some of the slides were hard to read. And we will hold a workshop on presentation preparation about a month before the next Bourne's. Help me to remember that I said that. Thank you. All right, we're going to start with the Churchill Sturgis Award for Outstanding Exploration in 2026. And this award goes to Matilda Borch. Who, I will note, presented 2 talks, one on a Churchill and one on a Sturgis. Congratulations. Again. Next, we'll do the poster awards. We have 3, starting with the 3rd place poster award, Carolyn Wexler. The 2nd place poster award goes to Deidre McGrath. And somebody give me a drum roll. Excellent. The best poster award, 1st place, goes to Amber Stokes. And I'll remind you that, let me congratulate you. Posters are done by 1st-year students who have yet to do their research, so the ability of all of them to do these great posters they did is really remarkable and a really good sign for their future work. We now come to our last category, the best presentation by a graduate student, and we'll start with the 3rd place, which goes to Andrea Terrell. I will set that aside. 2nd place goes to Elizabeth Rogers. And another drum roll, please. Thank you. The 1st place award goes to Avery Lamb. There was a special comment of approval. Well, thank you, everybody. I hope you all had a good time and learned a lot. I can't wait for the next one. Well, I can, but I look forward to it nevertheless. I hope you all have a good rest of the week and a good end of the semester. Take care. We are finished.